Please mute yourselves, everyone. All the participants are requested to please mute themselves.
And Nisha, since Professor Kajri Majumdar has joined, so you can get started with the proceedings as well.
Yes, sir. So, first of all, I request everyone to please mute their mics. Mark Twain once quoted, "Facts are stubborn, but statistics are more pliable." Worthy Chief Guest of the Day, Professor Kajri Majumdar, TIFR Mumbai, Honorable Director and Dean, Research and Consultancy, Professor Arun Kumar Khosla, Registrar S.K. Mishra, Respectable Professor K.N. Pathak, former Vice Chancellor, Punjab University, and adjunct faculty member to the department, Honorable Head Department of the Physics, Professor Arvinder Singh, distinguished faculty members, research scholars, and partakers. A very healthy and beautiful morning to one and all virtually present here. I, Nisha Chahel, would like to extend my warm wishes on behalf of the Department of Physics and Physical Science Society, NIT Jalandhar, and welcome you all for the workshop entitled Statistical Techniques for Data Analysis, which is a 5-day online workshop. The workshop is fully funded by DST SERB. The contents which will be covered in the workshop starts from the basics of probability and distribution functions. The workshop schedule brushes upon a spectrum of exciting and benefiting tools for various statistical techniques used for analyzing the data in all fields of management, sciences, and engineering. Now I would request the coordinator of the program, Dr. Harleen Daya, to share more details about the workshop.
Good morning, everyone. It gives me great pleasure to extend to you all a very warm welcome on behalf of the convener, Dr. Arvind Kumar, and coordinator, Dr. Sunil Dutt, in the Department of Physics, NIT Jalandhar, for this workshop entitled Statistical Techniques for Data Analysis, sponsored by SCRB, Department of Science and Technology, for the head social and scientific responsibilities under the research project, Fluctuations and Correlation, a hunt to QCD critical endpoint, with Dr. Arvind Kumar as principal investigator. We are grateful to the distinguished guests and speakers who have accepted our invitation for this course. I consider it a very special honor to welcome our chief guest, Professor Kajri Majumdar from TIFR, who has supported us in every manner and accepted our invitation at a very short notice. I have known Kajri since my Ph.D. days, and I still remember the energy and enthusiasm her presence would bring to any meeting or discussion. She was and still is a source of motivation for many researchers, especially women, with the way you carry yourself and project the image of someone strong and independent. I have personally found her to be most humble and modest. I am so thankful to you for accepting our invitation and agreeing to deliver a talk. I am sure the young researchers will gain a lot. We are truly delighted to welcome you here, ma'am. I am happy to welcome Professor Arun Khosla, Director and Dean Research and Consultancy, who has been instrumental in supporting all research activities in NIT Jalandhar. I am glad to welcome Professor K.N. Pathak, adjunct faculty in our department, who has given us the right atmosphere and support in all the academic matters of our department. I would like to extend a special welcome to Professor Raghunath Sahu, who has been guiding and supporting us since we first thought of organizing this workshop. We always felt he is one of the members of the local organizing committee. It's my pleasure to extend a cheerful, hearty and big warm welcome to all the colleagues and participants. We are without a doubt especially grateful that you are all here today. The workshop is a 5-day online event starting from 22nd November up to 26th November. More than 700 participants from across various institutes and universities have registered for the workshop. The workshop will focus on statistical techniques for data analysis in different areas of research. It will include the basics of probability and distribution functions. The topics such as error analysis, hypothesis testing, parameter estimation, Monte Carlo methods will also be covered during the workshop. The aim of particle physics is to understand the techniques used for data analysis. We have invited experts from across the country who will introduce the participants to the basic fundamentals, present status, and future perspectives in this area. So I will end by saying that the beautiful thing about learning is that nobody can take it away from you. So we wish that you learn from the talks here and apply the things in your life and research in future. Thank you.
Thank you so much, ma'am, for the information and your words. Now, I would like to request our head of the department, Professor Arvinder Singh, to motivate us with his kind words.
Yes, good morning, everybody. On behalf of the organizing committee, I welcome all the participants in this 1 week online workshop on statistical techniques for data analysis. I hope this workshop will help you in your respective research areas. Data analysis is the most crucial part of any research and in other aspects of life. Although collection of data is important, but statistical analysis help us to extract meaningful information from the data. My appreciations for the young faculty members of the physics department, Dr. Harleen Daya, Dr. Arvind Kumar, and Dr. Sunil Dutt for selecting such an important topic for this workshop. I am thankful to the eminent speakers who have accepted our request to act as resource persons in this workshop. They will enlighten you about the various statistical techniques for data analysis in different sessions of the workshop. And I really hope that you will take full benefit of their expertise. At the end, I wish you all the best. Thank you.
Thank you so much, sir, for your constant support and help. Now, I would like to invite our Honorable Director, Professor Arun Kumar Khosla, to enlighten us with his words.
A very, very good morning to all. Professor Kajari Majumdar, Chief Guest for the day. On behalf of my institute, faculty, staff and students, I extend a very, very warm welcome to you, ma'am. It's really our honor to welcome you, and I hope that your presence is going to be a big motivation as introduced by Dr. Harleen Daya for the participants. I also extend a very warm welcome to Professor Pathak, Adjunct Faculty, Department of Physics, NIT Jalandhar, Head of the Department, Professor Arvinder Singh, and I appreciate the efforts of Dr. Arvind Kumar, Dr. Harleen Daya, Dr. Sunil Dutt, and other faculty members in organizing this program, Statistical Techniques for Data Analysis. Data is everywhere. Like we say, data is the next fuel. So data we are getting, that is in a raw form. And when we make use of statistical techniques, when we make use of other similar techniques for data analysis, like machine learning and artificial intelligence, then we can have a very, very useful information, very, very deep insight into the data. And applications definitely are limited by our imagination because data is everywhere. It's not only confined to a specific department, a specific domain. So the programs like this, even I would like to attend this program because in our research also we are getting a lot of data. And this course is so relevant for every individual. So I'm sure the participants are going to be very much benefited because if you go by the contents of the course, it starts from very fundamentals. Even if somebody is new to this domain, not confident about how to make use of statistical techniques for data analysis, as shared by Dr. Harleen Daya about the flow of the course, the contents which are to be covered. So they're starting with from very basics. So I'm sure all the participants are going to be greatly benefited through these interactions. And these programs, they provide you good opportunity to learn new things, to have access to eminent personalities and to network with them. And obviously, so when we interact, when we collaborate, new opportunities they would be generated. So with these words, I again extend a very, very warm welcome to the chief guest of the day, Professor Kajari Majumdar. In a short while from now, you'll get an opportunity to listen to her. And my best wishes to all the participants and my gratitude to all the organizing team. All the best. Thank you so much.
I extend my heartfelt gratitude on behalf of Department of Physics for always being a motivating force behind organizing such workshops. Thank you so much, sir, for your support and help. Today we have with us Professor Kajri Majumdar as our chief guest. Professor Majumdar studied BSc with Physics Honours at St. Xavier's College, Kolkata in year 1984. She finished her MSc from University of Kolkata in 1986 and then joined TIFR Bombay as a Ph.D. research scholar. She worked in L3 international collaboration at the Large Electron Positron Collider at CERN. Later, she joined TIFR as a faculty member in the Department of High Energy Physics. India is participating in CERN LHC project from its very early phase, and she has been a very active member of this collaboration. She was a part of LHC collaboration during the top quark and Higgs boson discoveries. She is also putting her efforts to illuminate students about grid computing at LHC. Now I request ma'am to please address the audience.
Hello. Can you hear me?
Yes, Kajri.
Yes, ma'am.
Okay. So, yes. Tell me.
Yes, ma'am, you continue.
Okay. So, thank you so much for all the kind words. And I really appreciate the efforts put in by the organizers to make this workshop happen, because this is one of the crucial things we all need to learn. And as already mentioned by others, since we are more and more into data age, so we really have to deal the data properly and extract maximum information from the data we collect, which are quite often very time consuming and of course quite often very expensive as well. So it was very nice idea to have this workshop. I am going to talk about just very simple things, because I didn't have too much chance to learn about your level. Maybe I apologize that some of the things maybe you already know, some of them may be quite rudimentary. So I apologize for that. And I also have to apologize that it is not too much of derivation that I will do, because in the books you will get various derivations. So I will try to introduce the concept, so that in the courses given by others, it will be easier for you to appreciate what goes in. And as you all know that unless we do well in our research or in our studies, we don't feel comfortable ourselves. So how do we do well? We train ourselves, and during higher studies, it is our effort that makes us do well. It cannot be that we just go to the class and listen to lectures. So I request all the participants to really consult books, and various information is available, various materials are available on the web. So please go and study them, because I can do only a limited amount of discussion. So with that introduction, I try to start. Okay, let me share the slides. How do I do open share? Okay, share.
Manpreet, you stop the sharing.
Okay, then I first open my just 1 minute. Okay, so now how do I share it? Let me see. If I say close share.
On the top right corner, ma'am, there will be share content.
It says desktop window. Then
Just left to leave meeting sign.
leave meetings. I am in Ubuntu. So let me see. I have to keep the camera on maybe? No, not needed. I'm sorry, let me see. I open share tray, then screen share. Screen share, I should say this. Okay. And then I click her. I am not able to get the one of clicking. Share. Enter screen windows. No. Can you see this?
Not
Yeah, I'm sorry, I didn't try this before.
Everybody please share the
What to share?
screenshot
Not enter
so that
screen.
would be.
Chrome tab. It is not Chrome tab. Window.
Dr.
Okay.
Arvind, have you given the
Okay.
rights?
And it is.
Yes,
No,
yes.
I think now it is okay. Now it is.
Yeah. I have given that.
No, this is not. Yeah, have you got it? Not yet.
Yes, we were able to see it, see that for a moment, I think.
And it is this one. I'm sorry, I'm not.
Yeah, actually, we had seen that statistics.pdf thing. I think probably that's the name
that
of
is
the
what
file.
one.
Yeah, that we
But,
saw for a second, and but now we no longer see that.
Recording started. This is sorry. Opened desktop window. Then
One
I
minute,
say
I'll come to
window.
you later.
Then statistics. Then I say, but this statistics. Why should I? It is going behind my screen. Just a minute. This is the only one statistics. If I say this,
Dr. Arvind, if you have a presentation, we can share it from NRT side.
I didn't actually send it. I'm sorry.
Okay.
If I say share now, it is not happening. I can send it also, but
Yeah. So you have you downloaded this mean Microsoft Team, or you are using from from the web browser?
I have downloaded.
Oh, okay. Okay.
Now
So
I can't
let's see.
even. Let's see. Sorry. What about now? No.
It's visible.
Yes.
Now it is visible.
It is visible?
Yeah.
Okay.
Yes.
Okay,
is
sorry. I took so much time. Is it big enough?
Yeah, it's good enough.
Okay. Okay, sir. So, thank you again for the organizers to consider me to give this talk. I would like to just discuss some of the salient points of statistics and probability. So, because it's an introductory lecture, it will be at the very elementary level. Okay, we proceed. So we are mostly in particle physics. The participants are mostly in the area of energy physics, or coming from various other sources also, I guess.
From different.
Various disciplines, but unfortunately my knowledge is quite limited, so quite often I am giving examples from my area of research, that is high energy physics or particle physics, so please bear with me. I will try to say general things, and from there you can again extract the information and apply to your own specialization or own area of interest. So basically, of course, statistics plays an essential part in all sciences. So it's a tool which allows the scientist to treat the uncertainties inherent in all measurements and eventually to conclude from the results. So why do we do experiments? We want to measure something. And what do we want to measure? How do we measure? It's not just taking data. From data, we want to extract some information. Okay, and that is the result. And that result has two parts. One is a central value and another is the uncertainties, etc. So we will discuss more about it. Mind you, it is also a tool for planning and designing an experiment, taking into account the tolerances required for that apparatus, the time devoted for the measurement, the required precision, etc. So what do? We want to measure, say for example, the gravitational constant or acceleration due to gravity. So we have to think about an experiment, and this is a standard measurement. Some of you might have done it in the lab also, but we have to check what type of apparatus we are using, how crude or how refined the measurements are, how long are you ready to do? Maybe you have to do many measurements, so you want to just devote maybe one afternoon or maybe few hours, or you want to do it repeatedly and do the best measurements. So all that has to come into picture. And that is also needed when you want to measure, say for example, in this case G, with good precision. And then how do we do, what instruments we will use, how much money we have to get new or better instruments, all that will matter. Anyway, statistical methods are the tools needed to compare data with theory and to quantify the extent to which one stands in agreement with the other. So that you understand. So we have sort of in science two types of approach to understand the physical world. One is that we understand the physical world by doing experiment. Another one is that some people try to explain in terms of theoretical ideas. And those theoretical ideas will not be accepted by the community unless it is verified in experiments. So this is what I mean, that the experiments will be checking what the theory says, whether it is correct or not, and to which extent it is correct. So of course, one has to understand the physical basis of the models in the theory used for and which is being tested. So now while doing the experiments, what we do is that we typically observe events of certain type and measure the event characteristics. What do we mean by that? That when we say observe events, it has depending on the situation, the experiment we are doing, the definition of events may be changing. Just a simple one is that say for example during COVID time, you are checking how many students are entering the university campus. So you observe that, and from there you can then you try to check how many what are the temperatures and how what are the other characteristics of the students who you are allowing, and from there you say okay, 3% of the students maybe have high temperature, or maybe 1% of the students tested positive, and various things. And from there, you try to sort of get okay, so on an average students of this age group, and when they try to, in general time, let's say, they have so much probability of so and so. This is not very good example, but anyway, let's proceed. So the point is, in particle physics at least, events could be of various types. Say, for, I guess many of you have heard about experiments at LHC. It's a proton collider. Proton is colliding on proton in energetic protons, and they are energized to the extent of, say, for example, several thousand times the mass of the proton. And when they collide, because of this famous equation of E equal to mc square, we are basically smashing the energetic protons to get enough amount of energy, and from there we try to do various studies. So yes, some question? Okay. So now when these protons collide, there may be different types of processes happening, and we may be interested in a particular type of process. So when we say we are interested in a particular type of process, let's say we are trying to find out if there is a Higgs particle produced. Sometimes we may be interested in checking how many times electrons are produced. Maybe we want to measure how many times mu plus mu minus is produced.
Professor
so
Kadri,
this is, yes?
I think slides are not changing. Are you right?
Slides are not changing.
Yeah, it is at slide number 2 actually.
Yeah, it's in slide number 2. I'm in slide. You are able to see slide number 2?
Yes, ma'am.
Yeah, okay.
Fine.
So then this is what we mean by interactions in a collider, that we want to find the number of times, let's say one has collected data for about 1 year, and in that how many times in a proton-proton collision you have produced Higgs particle. How many times maybe there are oppositely charged muon pairs are produced. How many times electrons with certain energy is there. And so these are the types of interactions what we mean in particle physics. Or you all know that cosmic ray muon. There is from extraterrestrial sources lot of energetic particles, quite often they are alpha particles actually, hit our atmosphere, upper atmosphere, and there is an interaction at very high energies because extraterrestrial sources are coming towards Earth with very high energy, and then there will be a shower of particles produced, and in that shower of particles many things will be produced, but finally at sea level or at the experiment detector level in our laboratory we mostly get muons. but we want to see how many muons are passing through our detector. So we will see that what are the energy of the muons, what is the size of the detector, all that you have to take into account. But this is what we mean by what are the events. And in the laboratory, of course, in nuclear physics, you quite often you know that the large number of materials are not stable, and you try to find out that how frequently they are disintegrating. So you want to study the radioactive decay. So this is again another type of event, we call it. So from there, when we deal with this, let's say radioactive disintegrations. So you want to find, say for example, cobalt or cesium. Different materials will disintegrate through different ways and at a different rate, depending on the content of the nucleus. So when you try to do the measurements, let's say you are trying to measure the half-life, you take the, I'm sorry, there is a lot of noise. Is it okay, the noise outside? Are you getting disturbed?
No, it's fine, man.
Okay, fine. So you want to make a measurement, and so you try to, after that measurement, you try to interpret the data, and there what you need is the statistics. And then you try to do the extraction of the parameters. So you have to assume some sort of probabilistic way this this material has disintegrated, and from there, that's why you try to check the half-life, for example. And we start with a simple example. So what is the probability? Statistics, of course, deals with random processes. Even when we do the measurements also, they are essentially random. So classically, the probability can be defined using the symmetry property of the random device. So what do we mean by symmetry property? That means all outcomes are equal. All outcomes are equal means every outcome has equal weight. And when we do all these measurements, we call it a sample space. So for example, you roll a dice. A dice, of course, has 6 faces, so it can, let's say, simple one is like Ludo, etc. So there are various possibilities, and if you roll a dice, you get different numbers, and then you can see that how many times you get how many, what is the number as sum. So if you roll a dice, 2 can be obtained as 1 plus 1, and maybe 3, to get 3, we have 2 possibilities, 2 plus 1, or maybe you roll two dices. So, and to get 4, you can have 1 plus 3, 2 plus 2, 3 plus 1, etc. So the probabilities are equal, as shown here in this plot on the right hand side. So you are rolling 2 dices and you are summing up the value on the face, that is your D1 plus D2. And then you try to say how many times you are getting 2. If both are showing 1, 1, we get 2, and we can get 4 if one is showing 1, another is 3, and the time it can be 2 plus 2, etc. etc. So these are all random. It's not in our hand that in which phase the dice will come up. So we can define the frequentist probability as the probability to the fraction of times an event occurs. And let's say we are saying that what is the what is the probability for getting 6, total number 6 in the roll of 2 dices. So what we will do is that we will do this rolling of the dices many times. So that's what we mean, the limit of very large number. Sorry, there is a typing mistake. And so in repeated trials, then we try to count how many times we got 6, then we divided by the total number of trials we had. So this is a simple definition, we all understand. Now, as we say, that some tasks of data analysis include that estimation of the parameters, including the quantification of the uncertainty of the parameter. So whenever we try to say what is the probabilities, even for this type of thing, we have to say that what is the uncertainty. When we have done these trials, though we take the limit n equal to infinity, actually we will be doing it limited number of times. So there will be some sort of uncertainty will be inherent result. And we can also do in the data analysis that we test the extent to which the prediction of a theory are in agreement with data. This is what I was alluding to earlier. So we are talking about probability. So consider a set S called the sample space consisting of a certain number of elements. So to each subset A of
Madam,
S,
Madam, can I ask information?
Sure.
how we choose n to get the optimum result, the number, large number.
So the n can depend on your time you are ready to devote. At the time of, I think the rolling of dice is not a very good example, but in any other random experiment, you want to know the precision.
For example, you have macroscopic particle. Macroscopic particles. So how many particles should be large?
It depends what you want to measure. Let's say, can you just give an example that what exactly you want to measure?
I want to measure some correlation function.
So the correlation functions is related with the standard deviation. Okay, the sigma x.
Yes.
Each one how it is. So that sigma x, if it is a sort of random thing, then the sigma x will keep on reducing if you increase the number of observation. So in each one you measure, but say for example you are measuring correlation of two things. So one is occurring more frequently than the other. So you should consider most critically how well you want to measure the less frequent number. So accordingly the time you have to devote. But if you think that okay, that is not very important, you will be devoting less amount of time. So it is sort of relative that how large or how many times you will do the measurements.
So one cannot define large number.
Yeah, please. Please go ahead.
Can one define this large number precisely for any particular case?
Depending on the case in hand, that with what precision you want to measure. That is the critical part. If you say 10% is okay, let's say we are measuring the distance between the, what should I say? Distance between the earth and the moon. So we will be just measuring in terms of kilometer, and just 1 or 2 kilometers uncertainty is okay. But when you want to do the measurement for some, let's say between, let's say under the microscope, you want to measure the distance between two things.
Two atoms. Two atoms.
Sorry?
Two atoms. Distance between two atoms, let's say.
Two atoms, yes. So then it's your instrument also have to be very precise, and maybe there will be, though you say that you have measured the thing correctly, there will be definitely certain error.
Yes.
So that error, if you keep on increasing the number of measurements, that error will be divided by square root of n. So the sample variation will be less, because you are taking let's say you are making 10 measurements of the same distance between the two atoms.
Okay.
If you measure only once, you will have certain error decided by the instrumental error, where you have zeroed in. When you say that I have the distance between the two atoms, before I measure, I put the instrument at 0. But that 0 depends on what is the pitch. What is the minimum measure? You can say the like your scale. Is it clear?
Yes.
And then if you make the measurements 10 times, then you can take the average of the measurement distance of the between the two atoms, and then you divide by the square root of 10. So that will be the average distance between the two atoms. But if you do not have time, you are just happy with a large amount of error, it will be, let's say, I don't know, in angstrom or a fraction of an angstrom. But if you make many times a measurement, then it will be. So the point is that n will depend on the situation you are dealing with.
Okay.
For example, I want to measure, what should I say? Yeah? Tell me.
Actually, what there are lots of problems we are using for capturing the problems as
I am not able to clearly hear. Can you repeat, please?
Yes, actually there is a lot of problems. How we can understand according to the problem behavior, how we are able to we should apply the regression or correlation or any other method. Like how we can capture the problem behavior to select an appropriate tool to solve the particular problem.
If you can
Like
repeat, I'm sorry. Tell
some
me.
kind of problems are the probability. Some kinds of problems require non-probability sampling. Some kinds of problems require probability sampling. How we can get the
Probability
clarity
sampling.
about this behavior? Ma'am, how we can get the problem behaviors, and that will give us a proper screening about which appropriate method we should use, like regression, correlation, or multivariate. Which kind of methods we should follow?
Multivariate method, of course, I think it will be discussed later. Basically, when you see that the characteristics you are using for your measurements to get the parameter of interest, there are correlations, then you have to take care of the multivariate method. If you just say that, okay, you want to find out some characteristic in a class of students. So you first categorize, okay, maybe boys and girls. Then you say the age, etc. But then you say the height. Let's say you have taken students of class 4 or so. So sometimes some students are growing by height and weight various. So there may be sometimes some correlations. But then when the things are not very easily understandable, you go for multivariate analysis where you internally take care of the correlation. But this is again is not really a simple measurement. When you have a very tiny amount of signal along with a huge amount of background, that is where you want to beat the background. Okay. When you want to beat the background,
Madam, excuse
you
me.
try to
Madam,
find
sorry,
out the
excuse me.
characteristics.
Madam, please
Yes.
find some time for discussion at the last. Please, the last of our work. Don't put the discussion at the median. Please allot some time at the last time to discussion. So 15 minutes, 10 minutes, or 15 minutes,
Okay.
half an hour.
Yeah, okay. Or in the afternoon also we can do that. Fine, that is good idea. Okay. And so these are simple definitions. So the point is that when we do this frequentist probability, sorry, I was before that. So for consider a set called the sample space consisting of certain number of elements. Now to each subset A of S, one assigns a real number PA. We call it probability. And how do we do this probability definition? We have three axioms. For every subset A in S, PA should be positive or equal to 0. It cannot be negative. And for any two subsets A and B, if they are disjoint, the probability assigned to the union of A and B is the sum of the two corresponding probabilities. This is we all understand. And the total probability assigned to the whole sample space has to be 1. Is it clear? So the probability assigned has to be positive or 0. And if they are disjoint sets, then the total probability is the sum of them. But the probability of the whole sample space is equal to 1. And now I come to definition of frequentist probability. That relates probability to the fraction of times an event occurs. So that is again in the limit of very large number. And when we say the limit of very large number n tends to infinity, that is of course theoretical limit. So in practical case, again case to case basis, we have to decide, and that is what I have been referring to. So basically, the probability will be given by number of favorable cases divided by the number of trials. And it is only applicable, this is important for repeatable experiments. Then only we can do n number of trials. And ideally, of course, this is infinite. There is another type of probability, we call it subjective probability, that expresses one's degree of belief or credibility that a claim is true. So as the name suggests, subjective probability, one has to think about it, what exactly it is doing. It concerns the person who is doing the measurements, how much he believes for the occurrence of such a process. So a probability equal to 1 expresses certainty that the claim is true. Of course, this is how you understand. If we say the probability is 0, that means the claim is completely false. So the question is about intermediate values from 0 to 1. And that quantifies how strong the degree of belief that the claim is true. So of course, more towards 1, that means our degree of belief is very high, and more towards 0 means we don't particularly believe. So this definition is of course applicable to all unknown events or claims, not only repeatable experiments. Because it's the case for frequentist approach, you can say that we are trying to say that It need not be repeatable, but you can try to sort of guess from the person who is doing the measurements or person who is doing interpreting how much he believes in the truthfulness of the claim. So each individual have their own different opinion or prejudice about one claim. And so this definition is necessarily subjective. We will come to more about it. I am referring to Bayesian statistics. Anyway, so generally we can define the statistics as, again as I mentioned, that I will be talking mostly about the examples from the type of field I am working on, that is particle physics or related to nuclear physics also. So consider disintegration of particular radioactive source. And you take the measurements over a period of time. I give the same source or a similar source to you. You make the measurements and then we compare data. Let's say we do the measurements for 2 hours in the laboratory. So you do in Jalandhar, you get that okay, maybe 10 disintegrations have taken place. I do the experiment here in Bombay, maybe I get it the value 7. And if you do 100 times, you will see that mostly it fluctuates, but around a central value. So this is what we mean by the random process. And how do we now make a sense out of it? We try to say that this integration of a particular material follows a certain probability density function, follows certain rule of how it will disintegrate. Though at a given time, how many is disintegrating, that is completely random. So the outcome of a random process is described by a variable x, for example, which ranges across the admissible values of the process. So depending on the material property, if the material disintegrates very fast, maybe in 2 hours time we will get 100 or the whatever 50 whatever. But if the material has long half-life, so material disintegrates very slowly, and then it will be the admissible value will be much less, maybe maximum 10, 12, etc. So now the point is that we are talking about a variable which describes the randomness of the process, and this variable x can be discrete or continuous. I'm sorry, there was a question. Was there a question? Okay. So here on the right hand side, I just give a simple example of 2 types of distribution. One is that if the variable x is discrete, like we found, for example, for the dice. Okay, so this is a discrete variable. But sometimes it can be continuous also. And mostly we will finally encounter x variable where we can treat it as a continuous variable only. So this is say for example a typical example of say for example you are detecting muons through some detector, and you want to measure how much energy the muon has deposited in your detector. Let's say a scintillator, it scintillates, and then you measure the light, scintillation light, and from that scintillation light you try to interpret how much let's say its scintillator is 1 centimeter thick or 2 centimeter thick. So how much energy is deposited by the muon in the 2 centimeter thick detector, in this case scintillator. If we plot it, and then we will see that it follows some distribution. That distribution is described by some law, quite often we call it Landau distribution also. Anyway, so this distribution can be symmetric or asymmetric. If we go here, if we see here, this is a symmetric distribution, but there is no binding that it has to be symmetric. It can be asymmetric also. Anyway, given a discrete random variable n, the probability that can be assigned to each individual possible value, 0, 1, 2, 3, 4 in this case, so let's say n is up to 10. So that is given by P of n. Similarly, for a continuous variable, the probability Px is defined since it is continuous. When we say x, actually we mean the range between x and x plus dx. So this is the probability. We take a small, let's say, when we say at 1, being continuous, so we say 1 plus minus epsilon. In that range, we are trying to find the probability. So typically what we do, we try to find the probability density function. So this is what is given, the differential dpx dx. And this is the crucial part which defines the shape, the density function. And then when we integrate between two values, let's say between 1 and 2 or 1 and 4, we integrate that density, probability density function within that two ranges. So I was talking about probability distribution.
Excuse me, ma'am.
Yes.
Hello,
Tell me.
Ma'am,
Yeah.
can you use pointer, ma'am, instead of cursor, because to find these some points using cursor it is difficult.
How do I don't think I can do it. Sorry. Are you able to see my point? No, I am sitting on a desktop actually, on a Linux machine. So
Okay,
I'm sorry, I don't have a pointer. I was referring to this movement of cursor. Are you able to see?
Yeah.
Okay.
That's okay.
I'm
yeah,
sorry.
I'm able to
Okay.
see, but
Yeah, I'm sorry for my limitation. I'm not able to show the
But
dots
it's
with
clear.
the pointer.
It's a clear.
Okay, thank you. So now the probability distribution, I told you about separately. It's a discrete or a continuous distribution, but it can be a combination of both. So I don't know whether you know about Dirac delta function. So there, if we do the probability density function, we can have a delta function like this. At a given way, if x equal to 0, this delta function goes to infinity. At x not equal to 0, delta function is 0 actually. So if we take half of delta function and half of the probability density function, then we say corresponding to 50% probability, we have x equal to 0, as I told you. So at x equal to 0, we have the probability 1, but since we have this factor half, we say p0 equal to 0.5. And then 50% probability to have probability, or x 50% probability to have value not equal to x,
Madam,
and which is distributed according to fx. Tell me.
Madam,
Yes.
Madam, how do you know this half is delta function, half is?
No, this is our discretion. We are defining.
Okay.
It is our just for example. I am just giving that. Sometimes I just said it is a rolling of dice. It is a discrete distribution. But let's say you are taking in the university. Let's say height of all the students. There will be large number of students, and you can consider it. Let's say 5,000. I don't know in a 90 Jalandhar how many students are there. Many students. So if you plot it, say it will be it's a continuous distribution, and then if you say that okay, after some age the height does not change, then it will be maybe flattening down, etc. So for all practical purposes, when you do the measurements, quite often, even if we take discrete measurements, we end up treating them as a continuous variable. But here I am trying to say that how we will describe a distribution, the measurements we are doing, that we are saying it is distributed according to some function, and that function can be discrete, that function can be continuous. I will talk in the second half of the lecture in the afternoon. I will give some typical examples of various probability distributions, and it can be combination of both. And I just introduce some special function called the Dirac delta function, which is such that for the argument x not equal to 0, this delta function is 0 everywhere else, other than at the value x equal to 0. So then this corresponds to 50% probability to have x equal to 0, and 50% probability to have value x not equal to 0, which is distributed according to fx. I also would like to define what is called cumulative probability. Basically, you sum up. You take the integration. Quite often you do the cumulation or the summation starting from minus infinity, though the distribution may be defined within a certain range. Say for example 0 to 10 here in this case. But even if we take from minus infinity, let's say you want to do the accumulation up to value x equal to 5. So you will be integrating out from 0 to 5. Okay, and when we talk about some other distribution like Gaussian distribution, which is theoretically defined from minus infinity to plus infinity, so then we integrate from minus infinity to up to certain point. And the cumulative means, as the name suggests, that it will keep on increasing, and then you can see that the increment at, if you keep on increasing the range, will be very, very less because this curve is falling down. So that's why you can say that it was increasing and finally it is slowing down when you go up to 10. And what is it? The total probability is 1. So this is what it says, that if you keep on increasing the x, you integrate out, you go from 0 to 1, 0 to 2, 3, 4, etc. It keeps on increasing the total integrated probability.
It must be normalizable.
Yeah, actually the total probability should be always 1.
Yes.
So this is what we mean, that the cumulative probability sums up to 1. This is what the fx is. You can see here that f between x1 and x2, if you integrate out, and so when you take the total one, the whole range 0 to 10, it is summing up to 1. Of course, the probability density function can be defined if there are multiple number of random variables involved. Say for example, for n random variables, you take differential in n dimension, dnp x1 x2 xn, dx1 x2 xn. There is some mistake here, and this is my probability density function is f, small f, which is a function of n variables x1 to xn. So what are the characteristics of this probability distribution? As we said, by convention, that the distribution is normalized to unity. So if we take integral or if we take the sum, it has to be 1. So this implies that the probability of observing one of the possible
Ma'am, excuse me, ma'am.
Yes.
Ma'am, excuse me. Can you please switch on the previous page?
Yeah.
I will take a screenshot.
Oh, okay. Okay, I will share these slides later, but you can take this.
Okay, ma'am.
Yeah. And maybe may I request all the participants, please do not disturb the speaker except the questions, please. All the other things can be taken up later. Please, this is a kind request.
Okay, I go to the next page. Yes. So the characteristics of probability distribution, it means that the probability of observing one of the possible outcomes in a given trial is defined as 1. And this probability cannot be greater than 1 or less than 0. This is again repetition of what I have mentioned, but just remember this. It has to be definitely between 0 to 1. Now we do the measurements and we find a parameter x. What is the expectation value of x? So that expectation value of x typically is expressed through this notation. So this is nothing but the integration of x times the probability density function fx. If we take a discrete variable, then it is nothing but the sum of the product over all the bins I equal to 1 to n of xi and pxi. Here you are summing, and in case of continuous distribution, you are basically integrating out. And it need not be a simple variable x, but it can be a function of x also. And then the expectation value of gx, if the function is gx for example, then using such a definition, we again, x is distributed according to the probability distribution function fx. So the expectation value of gx is to be obtained by multiplying fx into gx and then integrating out. Okay. Now the variance. What is the variance? Variance is that, of course, you have taken a number of measurements. You have found out the expectation value, the average value. Here I am mixing up two things. One is for a whole distribution, what is it? And sometimes I'll be referring it to the sample of distributions. But just take it that variance is defined. I am sorry for so much noise. I don't know how to stop it. Just 1 minute. Let me go and check it. I'm sorry, in the next lab some construction work is going on. I should have requested them earlier. So in that case, the variance is defined as you can see the average value. Average is given in terms of this Bra and Ket, this notation of the square of the deviation of the individual measurement from the expectation value. So just again have a look at it. We are having n number of, let's say, measurements. We can find out the average value of that, and that average will not be rather the individual measurements will not be exactly the average. So there will be some variation, some dispersion. But if we sum up the dispersions, it will be equal to 0. So what we are saying, that how much is the dispersion, we will take the sort of norm, we square it and then we take the average. So that is called the variance. So x minus expectation of x, square of that, and we take the average of that. If we work that out, we can see here how this relation is coming to be for the variance. It is the expectation of the x square. Now you see this function gx here is the square of x. So this is the expectation of square of x and minus square of the expectation of x. This is the definition of the variance. And what we call standard deviation, then we take the square root of this variance. So sigma x, quite often we will come to that. That will refer to the uncertainty or the error in the measurement. That is the square root of the variance. So typically we assume that the measurement for a parameter are Gaussian distributed. There is a probability density function for the ith measurement, yi. Okay, so this Gaussian distribution we will talk in the afternoon, but in general when we talk about errors with a measurement, we just take it for granted that it is distributed Gaussian distribution. It follows a Gaussian distribution. Yes, questions?
Why did you assume Gaussian? Why did you assume Gaussian?
Okay, so I will discuss it in the afternoon. That it's quite often it's the law of large numbers. We assume that if we quite often we are not taking many measurements at a simple value of I. Let's say there are two variables. One is independent variable xi and another is dependent variable yi. Okay, fx you can say. Now at a given value of I, x, that is ith value, let's say, we are taking a measurement. That is my reading yi. Now, if 100 people take the measurement at the same value of xi and we plot this yi, we will see that it follows a particular probability distribution function. And that probability distribution function follows Gaussian distribution. So I am sorry that I am quite often referring to Gaussian distribution, but I am going to talk about it only in the afternoon. So that is the idea, that though we take only maybe 1, 2, 3 measurements, etc. I told you the other time when you are measuring the distance between two atoms, let's say 10 times your error will be less and so forth. But assume that at a given value of xi, you will be taking large number of measurements, and then when you plot those measurements, it will follow a Gaussian distribution. That is the assumption. That when we consider the error, that error follows Gaussian. It's according to that value yi plus minus delta yi, that follows the Gaussian distribution. So the mean and the variance of distributions are basically these are called the moments. So moments can be of any order. The rth moment of x about some fixed point x0 is the expectation value given as x minus x0 to the power r. And if r equal to 1, we are just talking about the sort of x minus x0, how much is the deviation of x from the fixed point x0. And 1 for r equal to 2, we take the square of the dispersion. So mean or average of x is defined as when r equal to how much, okay, I should not say like that, just take it for granted. I will talk about it later. So just the moment, just leave it as that, x minus x0 to the power r. So again, as I said, this is the mean. If you consider a distribution, when we take a measurements,
so madam, there can be higher moments as well.
Yes, yes. And in some of the analysis, yes, yes. Some of the analysis higher moments do reflect the characteristics of the physics involved. Okay. You can go 3, 4, etc. many moments.
Right, right.
Yeah.
So,
yes. Somebody asked another question? Okay, so we talk about measurements and the particular distribution it follows. So when we talk about the particular distribution it follows, we know that a particular variable follows A distribution which is characterized by some parameters. So this parameter, one is the average, that's the theoretical parameter mu. So it is the theoretically expected value. It is not the average of the measured values. When we say the measured value follows a distribution, so we are referring to some theoretical distribution. That distribution will have an average value. And this is the mu. And when we do the measurements and take the measured average value, that's my sample mean, and that is the estimate of the mu. Is it clear? When we prove that, okay, my measurements follow a particular distribution, and that distribution has a mean mu, and we take an average from our measurements also, then we say this average from the measurements is the estimate of the theoretical mean value. There's a mu. When we talk about the second moment, we take the expectation of x minus mu square. So this is the variance. So expectation of x minus mu square, if you go back to the previous one, remember this gx, you take fx gx. So similarly here, sorry.
The mu can be 0 as well, no?
Mu can be 0. Mu can be 0, and I will come to it how do we normalize also.
That's okay, yeah.
Yeah. So what we do is that my fx actually here I have written as px. Yeah, it should be fx. Truly speaking, I made a mistake here. It should be fx. So what you take is your gx is now x minus mu square. So you integrate x minus mu square fx, you dx, and you get the variance sigma square. And the square root of that is my sigma. This is the standard deviation. This is the measure of the dispersion or the width of the distribution. So when we talk about the width of the distribution, again we are saying how much is the fluctuation around the mean value mu. So I am referring to the Gaussian distribution. It will be clear when we come to the discussion of the Gaussian distribution in the afternoon. But basically we say that most of the, it's a bell-shaped distribution, symmetric distribution. Most of the measurements will be lying around my estimate of the mu value, that is the estimate of the average. Most of the time my measurements will be peaking at
what will happen to these results if distribution is not symmetric?
No, if the distribution is not symmetric, as you will see during this workshop, we typically fit a distribution. Let's say you are describing some distribution with a Gaussian distribution.
Let's say it's exponential.
It is exponential. Yeah, it's an exponential. Then that exponential will have some parameter, e to the power minus ax square, let's say, or minus ax. Or you are describing some distribution by a polynomial.
Yeah.
Fx equal to a plus bx plus cx square, etc. etc. So you will keep on trying things, and then you will say that there are characteristics called chi-square that will be, I think, discussed in by some other person, that using some measure of how good is my description is, we call it how good is the fit, goodness of the fit. You define a chi-square as the measured value taking the difference from the expected value, the fxi. It could be your exponential distribution, or it could be your polynomial distribution, or anything.
Chi-square same as sigma square, huh?
No, chi-square is not same as sigma.
That's a different.
That's a different one. No, here I am just talking about a different thing. Okay, let me come to how do you know which fit is done. So then you divide, you take the dispersion square at each point of measurement from the theoretical value. You divide by the error of the measurement at that particular point. Then you sum of that quantity for all the n points, n measurements you have taken, and then you try to minimize it. So that is, you define your chi-square, you try to find out by theoretical distribution whatever it is. So for whichever distribution the chi-square is minimum, you consider that is describing your measurement, your experimental data the best.
Least square method, yes.
Yes, you can say least square method also. In chi-square, we divide by the uncertainty, error in each measure. That's what we do. Okay. So, but here we are referring to the theoretical description of the probability density function, and that probability density function will have mu, the expected value. But always that will also have some sort of distribution with some sort of uncertainty or dispersion, and that is what we call standard deviation sigma. And that refers to the fluctuation around the mean value mu. See, let's say we know the mass of the electron. We have certain value. We know the mass of the proton. But whichever experiment we have used to measure the mass of the electron, there will be some inherent uncertainties. So there is absolute value, we may be able to measure up to say 5 decimal places. So that is very precise measurement. But there will be always some sort of uncertainty, and that uncertainty is the my deviation, standard deviation. So more precision means sigma value is lower. So it gives the fluctuation around the mean value. So when you take a distribution and you measure the same thing again and again and again, your measurement should be consistent with an average value with the theoretical value of mu. And the dispersion, what you have, could be either greater than or equal to or less than the theoretical uncertainty. But because measurements will have more uncertainties, it is very unlikely that you will have the uncertainty less than the theoretical standard deviation. So quite often it will be more. Say you know some parameter, theoretically it is say 5 plus minus 0.1. But quite often your measurements will have, let's say, if you have good measurements, maybe you will have 4.9 plus minus 0.23. Or sometimes you may have 5.03 plus minus 0.05. So if that deviation is low, that means your measurements are precise. If the measurement, the fluctuations are less in your measurement. And now let's say you are doing a measurement of something, and independently I am doing the measurement of the same thing. Different, there is no correlation. Then I give you the simple relation here. What do? We take the average, m1 plus m2 by 2. But what is the weighted average? We have to see that the uncertainties are involved. So then we just cannot say m1 plus m2 by 2. What we will do is that we weight with the uncertainties. Maybe I have done a measurement which is lousy measurement. My uncertainties are larger. So your sigma 1 is better, precision is better than mine. My sigma 2 is large. Then you look at this expression. We are not taking just simple average, m1 plus m2 by 2. I have to weigh my measurement according to the error. And if my error is large, my sigma 2 is large, that means the weight I will give to it is the weight it will get, my measurement, is less. That makes sense. That the measurement with better precision should get better weight, more importance. So if sigma 1 is small, that means 1 over sigma 1 square is larger compared to 1 over sigma 2 square. So that measurement which is more precise definitely should get more weightage. So that's why we call it weighted average. Weighted average is m1 by sigma 1 square plus m2 by sigma 2 square, and then you divide by the weight. What is the weight? Is 1 over sigma 1 square plus 1 over sigma 2 square. Again you can see here that sigma 2 square being large, the weight it will get is small. So this is my weighted average. And mind you, this is for uncorrelated measurements. And what is the uncertainty? This is the uncertainty. Uncertainty is 1 over sigma 1 square plus 1 over sigma 2 square. So if my sigma 1 is small, that means 1 over sigma 1 is large. And then my total uncertainty is small if I take the uncertainty this way.
That slide is
Than
not
individual
seen.
one.
That slide is not seen.
Slide is not seen. This one you cannot able to see.
This one is seen. But
Yeah,
next
there's the
one
last one.
which you are talking.
This is the last line, no? Last box. I am talking about weighted average M. Can you see the last bullet? If we have two uncorrelated measurements
I can
of a
see that.
parameter.
Ma'am, slide number 8 now it's showing.
I am sorry, I have not given the slide numbers. Yeah.
Yeah, this is okay.
Yeah.
This is
Actually, I prepared the slides in a bit of hurry, and I see that there are some mistakes, and I have not even given the slide numbers. So I take two measurements of the same variable. I make an average, m equal to m1 plus m1, and another person makes a measurement, m equal to m2 plus minus sigma 2. And then I want to combine to get the best measurement. Both of us want to do the same measurements. So this will be the weighted average. This is the expression I was explaining. And my uncertainty, since there are two measurements, two independent measurements, the uncertainty is better than any of them. This is what I want to say. So this is what you get.
Sorry,
Sigma
ma'am, are you talking about the sigma values in the previous slide, ma'am? Could you please go back?
Sigma value, yeah.
So
sigma value refers to the uncertainty or error or the dispersion. I will come to them a bit later more precisely. Tell me. Yes.
Deviation.
If we have sigma values less than 0 and if you square them up, it will become much more.
No, sigma value cannot be less than 0. See, that is the reason. You are taking the positive. Let's see this 1, 2, 3, 4. Second moment about the mean is available.
Square
X minus mu square. This is exactly the reason.
It is positive.
We are just taking the positive definite value. Not positive definite, is a positive. And then we take the square root of the variance. Yeah, continue.
By definition, it is positive.
Yeah.
It's a positive and a very less number. Let's say 0.01.
Yeah.
Okay. When you square it, it will become a very less number than that.
Yeah.
So if sigma is positive, the discussion that was happening there, if sigma is positive and we say sigma square is
not even when sigma is positive, 1 over sigma 1 square is a large number. 1 over sigma 1 square.
So the point I got from your explanation is sigma square is larger. But in a case where we have the
okay, maybe I was loose. What I mean is 1 over sigma 1 square. If sigma 1 is small, sigma 1 square is even more smaller. You are correct, less than 1. Then the weight is actually, I should write it. Weight is W given as 1 over sigma square. So that is why we call it weighted average.
Sorry, ma'am. So I heard it like...
No, I'm talking a bit loosely and I have not written the slides properly. It is the weighted average. I will correct the slides and then I will send it. So it is the weighted average and the weight will be more for the more precise measurement. That means where the sigma is less.
Smaller. Yeah, thanks, ma'am.
Okay.
Yeah, I just wanted to point out that...
No, that is true. Correct. Yeah. So I come to another definition called covariance. So as I mentioned that it need not be my measurement depends on only one random variable. There may be multiple random variables. And we try to find out what is the relation between the two different random variables for the same measurements. So what we try to do is try to find the relation in terms of what is called covariance. And this is the pairwise correlation. So when you say the covariance, what you take is the expectation value of x minus mu x times y minus mu y. So you have two, let's say here, the three random variables x, y, z, but you take two variables at a time, x and y, and then you define your covariance in terms of expectation value of x minus mu x and y minus mu y. But what is more important sometimes is not this value, but the correlation. We want to get to know that if I increase something, whether the other one is decreasing, or if I want to increase something, the other one is also, doesn't matter. It is independent. So that to get that, what we do is that we get the correlation coefficient as the covariance divided by the uncertainty, sigma x and sigma y. And since you are dividing, you can imagine the correlation coefficient will range from -1 to +1. This covariance expectation and the uncertainties are such that it will give me whether it is correlated or anti-correlated or independent. If it is anti-correlated, then If it is correlated, it is +1. It could be something else also, but positive value. If it is anti-correlated, then it will be negative. That is going down like this. R here, actually this is rho here. And then if it is not correlated at all with one another, then it's a flat distribution. X and Y will be just randomly distributed without any correlation, independent of each other. So that is 0. So now generally outcome of a process, no, this is, sorry, what is happening, just a minute. So now I am talking quite often of measurements and the uncertainties. I want to discuss more about these uncertainties. Measurement, we know what we mean exactly. So measurements of any kind in any experiment are always accompanied by uncertainties or errors. I think this has to be first understood. When we say that, okay, I have measured this is the value, that statement is not really complete until and unless we give the uncertainty involved with that measurement. So by definition, measurement is a random process. And as I mentioned already, described by some probability distribution characterized by parameters in which we are interested. So these parameters are of different types. One of the most common parameter is what is the average of the measurement, what is the dispersion in the measurement, etc., etc. But there could be some other measure. If it is some other complicated distribution, the probability distribution, there may be various parameters involved, and we want to measure those parameters. There was a question? Okay, I continue. So the results of a measurements are then samples from this distribution. Okay. Samples from this distribution means this distribution is a theoretical expression with which we are trying to describe the property of our measurements. And we have done some measurement and we are calling it a sample only because we are not doing infinite number of measurements. So it's a subspace. Okay, because it's a physical quantity. Not everybody is, I am making the measurement, so I am just taking a sample. And then we try to determine the theoretical parameters. So these measurement errors now can be considered as the sampling errors. In the theoretical distribution, we have the expectation value and we have the variance. And when we do the measurements, we are taking a sample of the whole space and then that measurement error is the sampling error. So in particle physics, there are various elements of uncertainty. So typically I can quantify them as, rather categorize them as theory which is not deterministic. In particle physics, that is talking about fundamental building blocks of matter in the subatomic world. So there we have to describe the physical world in terms of quantum mechanics. By inherently that has fluctuations, so that is not deterministic. There is a lot of uncertainty. So that is theoretical uncertainty. And the random measurements, when we do, definitely there will be errors. And that need not be, that is definitely not the quantum effects. That is just inherent with any measurement. So in addition, there will be uncertainty. Yes,
uncertainty is not measurement error.
No, it could be theoretical. No, the point is uncertainty will have various components.
Yes.
Various components. So one could be theoretical error because we are describing the process by quantum mechanics.
This is fundamentally because the quantum mechanics uncertainty is
fundamental. It's a theoretical. Yeah, exactly. Correct. Correct. So that is one component of the uncertainty, and we will call it theory uncertainty. But there are other there are random measurement errors. You are doing some measurement with some instrument, I am doing measurement with some instrument, there will be various errors. Even if we combine, that is what I tried to explain to you, there will be still weighted average and if we want to measure the same parameter, and along with it there will be some uncertainty associated with it. Even if the more precise measurement gets more importance, but there will still be some uncertainty. And then there could be some other thing which is not known to us. It depends on the experimental situation. So why my instrument is lousy? Why my measurement is not very precise? Maybe the instrument was not good. Maybe I did not wait for long to take data. I didn't have time, and so on and so forth. So there will be some systematic uncertainties with that also. And depending on the situation, in particle physics, there are many other components which come into the as the ones contribute factors contributing to the uncertainty. But I am not getting into that. So now we can quantify the uncertainty
This
using the
uncertainty can arise other than in intrinsic.
Yes, exactly.
How?
Exactly. Now, say for example, you have taken today you have done the measurement. Let's take just you have taken a length of the table. Now that scale, if the temperature there in your place is very small, very less, so the material of that scale, maybe it has expanded a bit. So each pitch value, let's say you have taken one scale and you have measured it's 9.2 centimeter.
But under
But
the
if the
same,
scale has,
but under the same circumstances, they must be same.
they must be same. But say for example, you have taken, I'm telling you, you have taken a measurement, it is 9.2 centimeter. And in summer, if you take, you may find the distance to be 9.15 because there is expansion if it is a metal ruler. Or somebody else has taken the measurement using calipers. So that measurement will have a better one. Pitch values are better. So the measurement uncertainties will differ. And similarly, you can say that how exactly you, instead of calipers, okay, I said somebody has done the, just taken a scale and done the measurement. The temperature. Or maybe you have taken many times and you have already done the average of that. So the average measurement is divided by the square root of number of times you have taken the measurements. So there will be experimental uncertainty, there will be intrinsic uncertainty, and then with the measurement there will be some fluctuations. And the theoretical uncertainty. So given all these uncertainties, we can say that probability, how it affects when we code the result. So the Bayesian method provides the important tool for analyzing these systematic uncertainties. So systematic uncertainties is that where the prior information may be available that does not necessarily stem only from other measurements, but rather arises from the theoretical arguments or other indirect means. Other indirect means what you have assumed. Say for example, you are measuring the distance. When you are measuring the distance, you have assumed, okay, it's a linear scale. But the point is that maybe some measurement is done which is not following a linear distribution. Take that. And then it has certain distribution it follows. But we have assumed that it's a theoretical distribution, but it may be some exponential function. So that prior information, it will vary from different arguments. You can say, no, it is good enough. I can say that it follows a linear distribution.
What is Madam Bayesian method? What is that?
So this is a subjective way of interpreting. That's what I am coming to it. So you have got a distribution. Now you want to argue that how is the distribution is, how you can describe it theoretically. So I will say I will describe it through a linear function, y equal to mx plus c. But you say no, it is a polynomial. I will try to find out. Let's say an exponential function. You have plotted in log plot. So log plot, it will be a straight line. But I have done a different way. And I want to describe it in terms of some polynomial function. So this is the prior information, how we are trying to describe. It's the theoretical argument, or I can have some other indirect means. So the Bayesian framework allows one to investigate how the posterior probability, how exactly one will infer about the measurements depending on what we have assumed in advance. So this is what I mean by prior probability. If I say that my dependent, the fx, is just a linear function, versus if I say my fx is a polynomial, that is my prior probability I am assuming. But then we will look into the data, and accordingly I will conclude finally that what my posterior probability is.
So, madam,
So I am assuming that a probability of certain given certain theory, how the experiment will be.
One clarification.
Yes.
Can we quantify the uncertainty using probability, the intrinsic uncertainty?
Yes. Again, I think I will come to it when we talk about the Safer Gaussian estimate. How much is the confidence? Quantum mechanical uncertainty, we cannot.
Okay, that is my question.
Of course, because this is inherent. But we have to take into account, say for example, in theoretical high energy physics, when we are measuring something, we are definitely keeping it in mind that there is some theoretical uncertainty involved. Say when we predict, I don't know whether you have heard about the magnetic moment of mu1.
Yeah, I have heard.
Yeah. So recently, of course, not you. I am referring to the students. So the magnetic moment of mu1, how it should be, and what the theory says, what the experiment says. So now theory says something which is not really matching with the experimental measurements.
So that's because quantum
mu1 G minus 2 experiment.
Yeah, exactly. So that is really raising our field now in high energy physics, that whether we are seeing something different than what we know till now, the theoretical structure, etc., or it is just that our theoretical calculations, theoretical predictions are not good enough. So even with that, you can say that this is my prior probability, that we are saying theoretically it is this much. It follows certain distribution. This is my theoretical estimate. And then we compare, when we compare, and there is some uncertainty that these are the effects I have not been able to take into account. There is some uncertainty. Say higher order calculations. Higher order calculations means when we talk about the quantum processes, there will be some simple process, a simple way, or there may be a complicated way, which we call there will be more, the coupling parameters will be appearing in powers of coupling parameters. So if we are not able to calculate those quantum diagrams, the amplitudes for those quantum diagrams, and so the total rate will be different, and there will be some limitation. We are able to calculate up to third order of coupling, let's say. So the uncertainty due to our inability to calculate the higher order processes will result in some theoretical uncertainty in the prediction for mu1 G minus 2. On the other side, if we assume my theoretical description is correct, I have a prior where I am trying to describe that when I do the measurement, it has to follow that probability distribution. But then I am adjusting, and then I can see that no, it is not the case. My posterior probability, given the data, is slightly different. So that is what we mean, that one investigates how the posterior probability is whether the data follows the prior probability we assumed, or it has to be changed, so that we get the distribution which is different than the prior probability we had assumed. So through this type of sensitivity analysis, the Bayesian result becomes valuable to the broader scientific community. Many more people will be interested in that than the particular one who have just calculated the prior probability. Means before we do the measurements, that is what we call the prior probability. We already say that I am going to do this experiment, I am going to measure this parameter, and this parameter is going to follow this rule. That is my prior probability when I say this rule. Whereas after doing the experiments, after extracting the measurement, when I compare, I see that no, my prior probability needs the adjustment. So after the adjustment, what we get, that is my posterior probability.
I have a question.
Yes.
When you have set up data,
yeah,
and you fit with some function, Can you be sure that this is a true representation of data, or there are alternative way of representing data?
Exactly. So let's say that you have a data and you have fitted something. So how will you say how good you are going to claim that my good fit is very good and my data is described by such relation? What you will have to show is you have to quote the chi-square value.
Okay.
Or then sometimes we say in high energy physics that confidence level. Again, in terms of Gaussian probability, we say I'm confident that 95% of the time if you do the measurement, it will fall within that range.
Excuse me.
Yeah.
Yes. Can I ask a question?
Yes, okay, though we thought we will ask later, but if it is relevant here, please ask.
Yeah. Only one question is that because I am having some doubt regarding this thing, because I am working in the field of clinical research. So how this dealing with the uncertainty is applicable in the field of clinical research while doing with the sampling?
So the point is that when you say that, okay, let's say you give an example, what type of research you are doing. Let's say you have taken a blood test of random people. People are going to a market. And you are saying that 2% of the people have sugar value above the normal. Now the question is, did you take a sample of 10 people or 100 people?
Yeah.
See, if you have taken a sample of 10 people, definitely the uncertainty with your measurement will be much larger. Then you cannot just say that, okay, 2% of the, out of no, sorry, these numbers are too small. Let's say you have taken, let's say you have gone to a stadium.
COVID
You are just checking.
Okay.
So large number of people. But you maybe the stadium has 4 entrances. You are taking data at all 4 entrances. But instead you are lazy enough. You are just taking the sample from the entrance of one particular entrance. So then your sample size is less. And from that sample size, if you conclude about something, that okay, from the people who have come, I see that 2% of the people have a very high sugar level and this and that. So that will give you some idea, but it will have to, when you quote 2%, you have to also give the uncertainty related to it. Whereas if you compile all the data from all 4 entrances, then you have 1,000 people. Then the uncertainty, what you have, is much less and you are more confident that you have sampled. When you say that, oh, you have not sampled enough, that means you have sampled large amount of sample space when you take more data. So if you give some example of your clinical research, what exactly you are doing, we can take more specific things, maybe at the end of this lecture. I'll be finishing soon.
Okay, thank you.
Okay, so I continue. So Bayesian statistics is it is the most commonly used interpretation for the subsets of sample spaces that are outcomes of repeatable experiments. So I will come to the repeatable experiment soon. So the probability PA is assigned a value equal to the limiting frequency of occurrence of A. Limiting frequency, that's if you remember, limit n tends to infinity. And this interpretation forms the basis of frequencies test. So we have done 100 measurements, out of which 2 has shown this result. But the subset of sample space may also be interpreted as a hypothesis. For example, I say that, okay, 2% of the people have diabetes so much. Here I have given an example for some other thing, that mass of the Higgs boson lies between certain range. So in the frequency interpretation, I just say either it is true or wrong. True or wrong means yes, definitely the mass of the Higgs lies between this range, or it can be no, mass of the Higgs lies outside this range. So the probability is either 0 or 1. Definitely within this range, that will be 1, and definitely outside this range, that will correspond to probability 0. But in the subjective probability, what you say is that it is probability is when you say degree of belief. That means you say 68% of the time, if I do the measurement of the Higgs, 68% of the time, the Higgs mass will lie within this range. If you extend the range by certain rule, then you will say 95% of the time the Higgs mass will lie within certain range. And mind you, when I say that you extend the range, then the probability or coverage also will be increased. Again, I will come to it in the afternoon. So basic point is that here you are doing subjective probability. When you say degree of belief, you believe that when I say my measurement A is equal to A naught plus minus delta A, that delta A typically corresponds to 68%. That if 100 times you do the measurement, 68% of the time your measurement of A will be peaking or within the range A0 minus delta A to A0 plus delta A. So that belief we have. This is a subjective probability. So this is a Bayesian theorem. We can say that probability of theory given data is proportional to what is it? Product. Probability of given data, given theory times probability of the theory. Then only we say that given my data, I see my probability, my theory, how probabilities. So what we say is that we assume first what we expected from the theory. That is my P theory. And then we check, we also say that given the theory, how much data is compatible. When we take the product of this, then we say that okay, given the measurement, given the data, my theory is good or not good. To which extent? That's the probability we try to get. So that is why we are assuming a priori, before doing the experiment, the P theory part. So here theory represents some hypothesis and data is the outcome of the experiment, of course. So this P theory before we do the experiment, this is my prior probability. So we believe that okay, my measurements will be following this distribution or following this theoretical description. And P data given theory is that probability to have gotten the data actually obtained given the theory, means the likelihood. If you have a theory and I have a different theory, then finally our idea will be that which theory is being preferred by the data. Agreed? This is my left hand side. Which theory will be preferred given by the data? Because data doesn't care whose theory it is. But to do that, we have to say what is the expectation from the theory in the data you are going to measure. So the expectation of the theory in the data we are going to collect, that has to be compounded with the probability that yes, this is the theory which describes the data. So P data theory, that's what I said, is the probability to have gotten the data actually obtained given the theory, which is called the likelihood. So Bayesian statistics provides no fundamental rule for obtaining the prior probability. This is important. There is no fundamental rule. That's why it is called subjective. Because nobody tells me that this theory has to be correct. You have a theory, I have a theory. Different theories. So it depends on subject. But we assume that and then we try to say that given that theory, how my data would look like. And then we try to compare that, okay, now given the data, whether that theory makes any sense or not. So Bayesian statistics, that's why once it has been specified from the above relation, we know how the probability for the theory must be modified in the light of the new data to give the posterior probability. That's what we will say, that whether your theory is better or my theory is better, that will be determined by the data. Isn't it? That will describe the physical world better. So your theory may be better. So that is what we will see. The data is better compatible with which theory. But to do that, we have to first assume that, okay, we have to believe in that theory. Then only we will be able to say that my data is going to be like this, given this theory. So given a straight line straight line behavior, I expect the data will be like this, follow like this rule. And given an exponential function, I expect my data to be follow this distribution. Then you combine and then you go look at the data and then you see what type of theory it is following. And maybe you have to tweak. Maybe it does not, it cannot be described by a polynomial, of order 2. Maybe you need a polynomial of order 3. Or maybe that is not enough, only the straight line is enough. So that is your posterior probability. So talking about, I told you that in this class mostly we'll be discussing not so much of the mathematical formulations, but I just want to give the basic idea about the Bayes theorem. So probability of an event A given B is given by this relation, PAB equal to A belonging to B and PB, probability of B. And similarly, probability of an event A given by B. Now from these two relations, we can say PAB times PB is given by PA intersects B, and but that relation we get from this. So finally Bayes theorem is given by PA given B is given by product of P of B given A times product of A. This was, remember, the prior, and divided by the probability of B. So PA is the prior probability, sorry, it should be PA given B has the role of posterior probability. This is the posterior probability. So application of Bayes theorem in a frequentist environment. I am sorry, again I give an example from the high energy physics. Let's say I am measuring mu1 using a detector.
How long?
And I told you my, sorry.
How long you will continue?
I have 2 more slides.
It's very long.
So shall I stop? Shall I stop here?
I think so.
I think it is better because you can have a look at the slides,
yeah,
and then try to understand that what we assume that our detector can do with how much efficiency it measures, how many times it will make a mistake. So from there, we will try to find out what exactly is the measurmental accuracy and how much confident we are that we have made a correct measurement. Maybe I will come up with a different example later. And then examples of probability that can be determined by means of repeatable experiment. That is where we do the frequentist one, when we say we can repeat the experiment. So when we do the experiment, repeat and repeat. Well, let's say we are playing with the cards, deck of cards, so we can keep on shuffling. And then what is the probability to win a lottery? So though a specific lottery extraction cannot be repeated, we can imagine to repeat the extraction process using the same device and the extraction procedure. Similarly, I told you about the identification of mu1 there, where there is a pi and another particle can fake. And here I am talking about electron and photon. I am not getting into that because I have lost time. So if you remember, Higgs particle was discovered back in 2012, almost a decade back. So now you look at the data. Data has a lot of fluctuations. These data points are the black points, and the uncertainties are given by these error bars. Very large number of error bars. Now you can say, I am claiming the Higgs particle to be of mass 125 GeV. So there is a red curve. By trying to explain my data distribution, this distribution of these black points as a sum of green distribution, blue distribution, and the red curve, I say my data describes it best. If I do not have the red curve, I cannot describe my data well. Okay. My data has a lot of uncertainty, but still, given the uncertainty, I have to introduce this red curve to show that fluctuation on the higher side. And by doing this, I assume that yes, my Higgs particle exists, and given the way we have done the experiment, how many such events, Higgs production and then it is decaying, etc., we will be seeing when we have taken data over a certain amount of time. All those details are given here. And with that, then I have a theory description how I will see in my data. And that theory description, that what I will see in data, is given by the red curve. And now you see we have done this experiment, and we see that yes, this theory is able to describe my data behavior. And if I say my Higgs particle had a different mass and it will have different thing, maybe I will have some curve here. But I will be able to tell you also from here that no, such a curve is not described by the data. My experiment is the ultimate decider, which is correct or not. So given this type of behavior in data, it was claimed that yes, there is a Higgs particle and Higgs particle was discovered using such a final figure or plot of discovery plot. But the question is, yes, we can say that we are so much confident that if we repeat the same experiment within the same running condition, we will get some result. But if we ask the question, what is the probability that the peak is due to a background fluctuation instead of a new signal, we are not able to repeat that case because fluctuation again is random. Like the way it has fluctuated here, some other points could have also fluctuated up and down. And since these fluctuations are random, even if I do 100 experiments, where the fluctuations will occur, we do not know. So if we ask a question, what is the probability that the peak is due to the background fluctuation instead of new signal? So background here is given by the blue and the green curve, summation of them. And their fluctuations can give me some excess. We are looking at the excess of events. So that is not a repeatable case. So I give you some more examples which is not repeatable. This is a standard example. What is the probability that tomorrow it will rain in Jalandhar? So the event is related to a specific date in the future and the specific event cannot be repeated. What is the probability that your favorite team will win in the next championship? Though every year there is a championship, a specific one cannot be repeated. Similarly, there are other one. What is the probability that a dinosaur went extinct because of an asteroid? That's what we believe. We believe that, but it is referring to an event which occurred long back. And we do not exactly know. We have no way of knowing what exactly happened there that caused the dinosaurs to extinct. And similarly, various other things. What is the probability that climate changes are mainly due to human intervention? This question is related to a present event whose cause is unknown. So these are not repeatable ones. So here, these are the cases when you try to interpret, we have to assume Bayesian probability. So I will stop now. I am sorry for the time taken. And I will try to come up with definite examples and definite distributions in the afternoon. Thank you.
Thank you so much, ma'am.
Thank you so much.
Thank you so much, ma'am, for this informative talk. Ma'am, with your permission, can we proceed to the questions for the session?
Yeah, sure.
Okay. Anyone who is interested to ask any questions can please unmute their mics and ask the question.
Ma'am?
Yeah.
Ma'am, I want to ask in the context of gamma ray burst that there is a high source of intensity, especially in the short gamma ray burst, but for a very short interval of time. So how data can be accessed here?
So the point is you are looking at the
Bayesian methods are used or any other?
Yes. So you are looking at the photon spectrum, isn't it? You tell me how exactly you are doing the experiment in the gamma ray burst.
Ma'am, currently I am studying, ma'am.
Okay. So the gamma ray burst means gamma refers to the photon, and you are saying that okay, some source is there which is suddenly giving lot of energetic photons, and those photons you are trying to find the source. But if we look at when we do the astrophysical measurements, quite often we are measuring the photons. Let's say their energies, their angular distributions, etc., etc. So we have a background measurement. And on top of it, we are saying that suddenly from some source, some additional photons were emitted. Those are the photons we are seeing above the background. So it is exactly like the Higgs discovery plot. There is a background and we are seeing some additional source. And that source distribution, here we are talking about the mass of the say 4 leptons, etc. Don't bother about that. Let's say gamma ray energy. You have an energy spectrum defined some way through some say polynomial. And now you are seeing that the way you have described it without the gamma ray burst event Your data is not following that description. Then you assume that there is a gamma ray burst. That is your prior. And then you assume if such a gamma ray burst has taken place with so and so parameters of the source, and then I am making the measurement. So this is your given theory, what is in the data. Where it is gone. Given theory, what is in the data you expect. So then you check that, how it is happening. Same thing is here. I assume, I believe that there is a Higgs particle produced of certain mass. Given that certain mass and the way I am doing the experiment, both have to be taken into account. Both have to be convoluted. That given Higgs particle, what is the production rate at LHC, and then how we are measuring. When we do that, then we have some distribution expected. This is the red curve. And now we are seeing, given data, whether the theory is able to tell correctly the nature of the data. So here we say yes, data is able to explain additional source of 4 leptons by assuming that there is a Higgs particle of mass 125 GeV produced. So same thing here you will do. You will find out the source of photon, various sources of photon for example, and then you try to say that I have a distribution of background, and then unless I put in the additional source of gamma ray burst, I cannot explain the data. Is it clear?
But ma'am, as far as I've read, we are not still, we didn't get the source of gamma ray burst.
Yeah, so that means you will be not able to explain. That means P theory to start with will not be applicable.
Okay, ma'am.
You have to assume that there is a gamma ray burst is happening. No, there is a source which is giving me gamma rays. So that is your, this is the one that subjective probability. I say that okay, there is a gamma ray source. You say there is no gamma ray source. Then in your observation, you try to explain the observation.
I'm saying, suppose there is a gamma ray source, but
yeah. So you will explain in terms of that unless I put in that additional source which is giving me excess of events for the gamma rays, I cannot explain the data. What is the exact nature of the gamma ray source we do not know. I am aware of what you are referring to, but in general I'm saying.
I'm referring to the progenitors of gamma ray burst.
Exactly. That is not known, that is true. That is one field of research. What will give such energetic photons.
Okay, ma'am. Yes, ma'am. Thank you.
Any other question?
Hello, ma'am.
Yes.
I have a question. How can we distinguish between continuous and discrete variable? Means, if in realistic case, if I have a radiation source, it can emit any type of energy value radiation, but it can emit.
Any type means how it will be? It will be decided by the Q value.
It will be decided by the Q value, but it will.
What is the mother particle? What is the daughter particle mass, etc.? Which are the other particles, etc. Fine. Okay. Still, you say any type. Fine.
Yes. Means, but it will emit the radiation continuously.
Yes.
Then.
So that is radiation continuously means you will be measuring that radiation.
Yes.
So you are measuring, let's say 1 hour in the lab. You have a detector, and with that detector, you are saying how many counts are there.
Yes.
Okay, like let's say Geiger-Müller counter. Just very crude way I'm just saying.
Yes.
So you are detecting in 2 hours time 5 events.
Yes. Then
I am taking that same source. I have my own Geiger-Müller counter. I measure. I also do 2 hours. I may not get 5. I may get 2 counts. Somebody else may get 7 counts.
Yes. Then what will we say this count? Means it is discrete variable
No.
or a continuous variable?
In principle, it is discrete variable.
Number of count?
Yeah, in principle, you are correct that you have taken a discrete variable. But when we say that it is following a radioactive decay law, etc., let's say it's say cesium or cobalt, it has half-life so and so. We are assuming that we are doing large number of measurements, or large number of people are doing the measurements of the same source, and there we are assuming that these counts also, somebody gets 5, somebody gets 6, somebody gets 7, etc. Okay, whole thing if you plot, whole sample,
Okay.
the sample size is large, then you can treat the count as a continuous variable.
Okay. Means for continuous variable, the data set should be large, very large.
No, it depends. It depends on the context.
Okay.
It depends on the context.
Okay, thank you.
Ma'am, you said about the
Quite
books.
often actually things are continuous, you can say.
Ma'am, you said about the books.
Which books?
About understanding of probability theories.
Okay. I will give the references.
Okay, ma'am. Thank you.
But the more than books, quite often you will see on the internet there are lecture notes also. So I know about the books meant for particle physics, but I understand the students here, participants here are not mostly particle physics. So then I have to search for
we
it.
are solid state physics, condensed matter physics.
Then maybe the organizers can they just find out some books, and then later after that, at the end of the workshop, one can find out. We will try to provide some material.
Okay, thank you.
Okay.
Yes, so is there any other question by the participants?
Yes, we do see one more hand raised by Himangi Verma. Himangi, please go ahead and ask your question.
Yes.
Yes, in the chat box there is one question by Deepika. Deepika, are you there?
Chat box. Shall I stop sharing? Then maybe it is easier.
Yes, sir.
Okay, I am. The question is why the error in measurement follow Gaussian distributions? This is the question here.
So this is the law of large numbers. Law of large number means though we do only limited number of measurements, in principle if we assume that we are doing large number of measurements, and those measurements when we plot, then we will see that the central value what is measured, there is a symmetric distribution which is peaking at that central value, the average value, and the spread in measurements follows a symmetric distribution with certain width. And given this mean value and the width, we can describe the measurements to be following Gaussian distribution. So I think introducing Gaussian distribution is very important. So in the afternoon it will be clear. So essentially we measure, though given an independent thing, we measure certain value. We assume that if we do large number of same measurements for same input, those measurements will follow Gaussian distribution. So the uncertainties are according to the Gaussian distribution. For a given input value. So for each independent input value, I will have n number of input values, input points, you can say measurement points. I have n expected measurements and corresponding uncertainty. For each point, the distribution, there will be Gaussian distribution.
Yes.
But there are certain cases, I will explain that in the afternoon. If the number is small, etc., it will follow an asymmetric distribution described by, let's say, Poisson distribution. Like I told you that Higgs particle. Okay, I will talk about it in the afternoon.
Thank you so much, ma'am, for addressing the
Hello,
questions of the audience.
Hello.
Yes, please. Yes.
Ma'am, this is Shamim. I am a Commonwealth scholar with kind permission from you. May I please ask my query from Honorable Ma'am, please?
Yeah.
Thank you very much, ma'am, for being so kind to me and allowing me. Ma'am, actually, that Bayesian, distribution.
Oh, there are
Okay.
a lot of questions. Yes, sorry.
Hello, ma'am. That particular, Bayesian, distribution. Would you please be kind to refer me any good books on that so that I can actually, study a bit more about that particular topic, please?
Okay. May not be today because I have something else after lunch, and then we have the lecture at 3 o'clock. Afterwards, towards the end of the workshop, I will share it. Okay.
Thank you very much, ma'am. Thank you very much.
Maybe I will modify also some of my lectures because I see there are some thing I have to put more, and then according to it at the end I will give. Okay. So there was one question in the chat box: how to interpret statistics for the image processing? Give some brief about it. What type of image for Rajesh Kumar? What is the image you are processing? Maybe he is not there. Okay. Chest X-ray. Okay. You are doing chest X-rays. So what is the uncertainty you are doing? When you do the chest X-ray, how do you process the image? No, chest X-ray for COVID you are doing, but how exactly you are processing the in terms of the difference in the density, means how clear the image is,
Rajesh,
how much is the
can you
haziness.
unmute yourself? That will be fine.
So, say for example, if we have for a clear chest for a healthy person, we have some idea. And now for an unhealthy person, a sick person, we take the chest X-ray and we see when the doctor says there is a patch. What does he mean? That he compares the dispersion, or you can say that he has some idea about how the cleared chest X-ray will be good person's, healthy person's chest X-ray will be, and compared to that X-ray, compared to that X-ray image, how much it is. So therefore, in the processing, you will find the density. Say for example, you consider pixel by pixel, and you find the density, and you try to find the difference in density with respect to your theoretical description of a healthy person. And if that density is large, the dispersion in the density is large, then you see that that means there is some infection. So the chest X-ray is more hazy, or there are patches in the X-ray. If the density is low, then your hypothesis that the person is healthy is correct. So if the density is large, you rule out the hypothesis that the person is healthy. You say person is not healthy. There are patches. Broadly, that is the case. But typically, you assume some functional form, how the density will vary from pixel to pixel, in the sense you take, let's say, 1 millimeter by 1 millimeter square. And you for compared to the rib bone, how from the distance, or how you go from maybe from left to right, top to bottom, how it will be. So you have already a matrix of a clear person's chest X-ray. So you have a map, like the India map. India map, you have got a different states with different colorings. And then you have got a map with different colorings and different borders. So you find the difference of the borders, and you find the difference in the colors, and from there you test your hypothesis whether which is correct or which is not correct. this map brought by somebody else is correct or not. It's like that. Okay. So some tools for qualitative data analysis will be discussed later by others in the coming days. Maximum likelihood fit, etc., etc. Hypothesis testing. So I am not going into that because that is why it is a 5-day course. So I was to introduce only the basic ideas. And now I will talk about the basic distributions. Poisson distribution, binomial distribution, etc., etc. Gaussian distribution.
Thank you so much, ma'am, for addressing the questions. Thank you so much to all the participants for being so cooperating. So we'll meet at 3 p.m. for the next talk. And for the
By the way, can you meet a bit later? Is it possible? Or do you want to keep it at 3 only?
It's possible, ma'am. Kindly suggest at what time?
3:30 because I have something else after lunch. So I do not know how long it will be. So I don't want to be under tension. Will 3:30 be okay?
Yes.
Something has come up today only. Okay. So if it is not too inconvenient, I am sure all of you are busy with so many other things. But if it is sincerely, I see there is no other lecture. So if it is not too inconvenient, I will like to start at 3:30.
Yes, okay, no problem.
Okay.
Okay, thanks, ma'am.
Thank you. I'll see you at
slide. I
will just send the
kindly
slides.
share slide.
Yeah.
Okay, thanks.
Not today because again I told you that there is something else. I cannot make sure that the slides are all here. Afterwards, I will just send it in a day or two.
Okay. Thanks. Thank you.
Bye.
Thank you, ma'am.
Thank you so much,
Thank you, ma'am. Thank you so much.
Okay, so please note down all the participants will be meeting at 3:30 p.m. to continue the talk for the day.
Yeah, and
thank you
we will definitely be putting a message in WhatsApp chat as well. Thank you.
Yes, sir. Okay, thank you, everyone.
Thank you, sir.
I request everyone to please mute their mics. Uh, I request all the participants to please check if their mic is muted or not. So please mute it.
अब जो है वो फाइल कर देंगे पूरी क्लास को ही। इट इज नॉट दैट वे। मैंने आपको पहले कहा था, कल के बाद आप ठीक होंगे सर। ठीक है।
I kindly request Sanjay sir and Himmat sir to please mute their mics. It's 3:29. We'll start just in 1 minute.
Hello, have you given me the sharing rights?
Good afternoon, ma'am.
Good afternoon.
Ma'am, it is with
Just a minute,
Arvind, sir.
just a minute, please wait.
Good afternoon, one and all. I welcome you all to the second session for the day. Probability has become one of the basic tools of statistics. Sometimes statistical analysis becomes paralyzed without the theorem of probability. The theory of probability provides the foundation for statistical inference. In general, statistics can be considered as offsprings of theory of probability. It builds on its parents and extends the area of patronymic jurisdiction. So I invite ma'am to please start the talk. Ma'am, are you able to share now?
Thank you. Let me try. Yeah. I hope I can do that. Is it okay? No?
Ma'am, I'm not able to see your screen.
Just a minute. Oh. Every time this problem is there. This one is there, then if I say share, why it doesn't? What about now?
Yes, ma'am.
You
It's all
can.
right.
Okay.
Yes, ma'am.
So, good afternoon, everybody. Thank you for coming back again. Though I was not very happy the way I presented the topic in the first session. Anyway, so let us continue. We were talking about measurement and the errors. So, measurement of any kind in any experiment are always subject to uncertainties or errors. There are two types of errors. We started
Sorry to
referring.
interrupt, ma'am.
Yeah.
Ma'am, I think you can maximize your screen and minimize the.
This one, no? Okay, let me see.
Yes, ma'am. So it will be full screen then.
What about now? Is it okay?
Yes, ma'am. Yes, ma'am.
Okay.
Sorry.
So, talking about measurement and the uncertainties, there are two types of errors, systematic and random. So, systematic errors are uncertainties in the bias of the data. For example, maybe you are using a voltmeter and you have to first zeroize it. And if not done properly, what happens? All measurements will be shifted in one direction, unison, by the same amount. So, this is in contrast with the random error, which indicates fluctuations of individual measurements. So, independent of others. So, this is systematic, means systematically things are getting biased in one direction or the other. But the point is, okay, we can zeroize the voltmeter, but the zeroing can be done up to certain extent, within some value, okay. Maybe that is decided, of course, by the precision of the instrument you are using. So this value, even if it is small, it is non-zero. And that value sets the limit for the degree of certainty in the measurements. And hence the conclusions drawn. Again, it's like the pitch value. How much is the minimum you can go to? Anyway, there is importantly, there is no consistent method of estimating the systematic uncertainty, because quite often even the sources cannot all be identified, let alone the measurement. So, given all this, we are not going to talk about systematic uncertainty, because for a given measurement of a certain type, one has to worry about the systematic uncertainties. So, for the next 1 hour, I hope I will finish in time this time, today afternoon. We will talk about the other types of error. But before that, I thought we will talk about the, roughly we have talked about the other type of error, random error, etc. And I will talk about the distributions as planned. So, random errors are handled by theory of statistics, and they arise from instrumental precision or from inherent statistical nature of the phenomena being observed. Both are treated in the same manner as uncertainties arising from finite sampling of an infinite population of events. So, I would like you to appreciate this, that we assume that there is an infinite population, but due to various limitations, we do the measurements on finite population, okay, and using finite sampling, maybe only once or so, not twice, like that. And so the random errors are arising could be due to instrumental precision or due to the inherent statistical nature of the phenomenon. And so sampling is the experimental method by which information can be obtained about the parameter of an unknown distribution. So we want to measure the mean value or something like that, or how it is following a particular law, the linear or exponential, etc., etc. So the given data sample, one tries to find, given a data sample, one tries to find the best estimate of the parameter. So the measurement of a fixed quantity involves taking a sample from an abstract theoretical distribution determined by the imprecisions of the instrument. That is what I was referring to earlier. And the instrumental error is treated as a Gaussian error. So I am coming to the Gaussian error soon. But the point is, sample variance, you can call it a square or so, of the data x1, x2 up to xn is defined as, earlier we were defining in terms of square, but look at this, the variance is now, hello, can you hear me? I will talk
yes,
to you later.
Yes, ma'am, you are audible.
Hello? You can okay, fine. So the binomial distributions, we start with the simplest one. Again, we come back to the coin. Okay, so coin only has two faces, either back or the number side or head or tail, whatever you call it. And probability to obtain either of them is half. So that is a simple one. And then what is the binomial distribution? It gives the probability to achieve n successful outcomes on a total of n independent trials, whose individual probability of success is p. So how many times I will get ahead if I toss the coin for 100 times or so. And that is given by this expression. F n capital N P is the factorial n, and this we anyway I think from childhood all of you have been doing about it. 1 minus P is quite often called Q, etc., etc. And so the mean again, the expectation value is given by xfx, and we call it mu or whatever. And this mu will be n capital N times P, the number of trials you are making, and P is the probability for getting it. The variance is given by NPQ. This is the variance. So capital N times P times 1 minus P. So what is a typical example? Let's say that we are using a detector with efficiency P, and N is the number of detected particles over total number of particles N that cross that detector. So this is a simple example where we do either it detects or it does not detect. It's only yes, no possibilities. So binomial distribution corresponds to the situation in our experiments where we have only either it does with some efficiency or it doesn't do. It cannot do. That's how it is done. I come to points of distribution. So they are in case the P here was the probability for success, you can say, or for the coin, of course, P is 0.5 and Q is 0.5, but it need not be the case. Anyway, sometimes it can happen that the success rate is very, very small. So if that is very small, but still we do large number, n tending to infinity, then NP is finite, and let us call it nu, where equal where NP equal to nu, actually this is, where nu is some finite value. So the binomial distribution in that case becomes a Poisson distribution in this limit. Now n is an integer, non-negative random variable. Okay, so I will tell you how it is done. Say for example, you are standing at the bus stop and you are just checking number of cars passing by. Red cars are given by a certain make, Honda car or whatever. So you try to do this. And this is expression for expectation value. There, first of all, we should look at the probability density function. So there is only, you are doing n times, and the average is nu, that is NP. So then it will be given by nu to the power n by factorial n and exponential minus nu when you are doing n trials. And the expectation value is nothing but n into fx, if you remember our earlier expression, earlier definition. So that is nu. And interestingly, the variance, that is also nu. For variance again, you do n minus nu. N is like your x and nu is like your mu, and the stick square is like the moment with r equal to 2, which I defined earlier, and then you multiply with fx, so you get nu. So basically Poisson distributions model the number of occurrences of random event uniformly distributed in a measurement range whose rate is known. So the rate is known, which is small, and this is uniformly distributed. It's the number of raindrops falling in a given area and in a given time interval, or the number of cosmic rays crossing a detector in a given time interval. Now importantly, the Poisson distribution may be approximated with a Gaussian distribution having again the same thing. For Gaussian distribution, we say the expectation value or mean is mu. So in this case, mu equal to nu, and the standard deviation sigma is square root of nu for sufficiently large values of mu. And what is sufficiently large value? So you can see here the distribution, the Poisson distribution for various values of nu. From left side it is nu equal to very small mu 1, then various nu is increasing here accordingly. And you can see it was skewed, but slowly it is becoming symmetric also, and it sort of assumes a distribution like bell-shaped symmetric distribution, that's like Gaussian. Also importantly, the nu is increasing here. But remember one thing, after all it is supposed to be asymmetric distribution. So this peak value does not correspond to the mean of this distribution. When it is large, say for example greater than 20 or so, a peak value may roughly approximates the mean value. So this is say for example for 30, this is for 20, etc. But otherwise for lower values it will be asymmetric. So this corresponds to the usual distribution of events in particle physics. What do we mean? Say for example in LHC experiment we are colliding protons, and how many protons are giving me Higgs particles or something. So the large number of collisions are taking place, that's like your capital N, but the occurrence which makes the Higgs particle be produced in the laboratory, that is very, very small. So that is why P is very small, but NP is finite. So that is the idea in particle physics experiments. And for large mean values of nu, the Poisson variable behaves like the continuous variable. Though here we are considering nu as discrete. Okay. So as was mentioned in the last class, that quite often we take them as continuous. So there also we are assuming that the is large number of observations or large mean values here nu. So this is of practical importance. So I come to the Gaussian distribution. This is important and it is used in a large number of cases. So what we do is that this is applicable for large number of events with mean mu and variance sigma square of x. X is again a random variable distributed according to this probability density function. 1 over root over 2 pi sigma square exponential minus x minus mu whole square by 2 sigma square. So here is the x value, okay, 0 to or minus 3 to plus 3 here. And its positions at 0. For the timing you just consider this. But usually it can be anything. So let's say it is x0. And if you plot this function, you will get a symmetric shape because it is x minus mu square. So because of the square, it is symmetric with respect to x. And this sigma, standard deviation, is related with the full width at half maxima. Full width of half maxima is slightly greater than 35%, rather it is 2.35 times sigma. So you can see here this is the sigma. And when we generalize to n dimensions with mean mu and covariance c, we can do like this. 2 pi, instead of for single one it was rather variance for sigma, and then if we take the covariance matrix, then we do it through this n by 2 and exponential minus of x minus mu, this is transpose, and this is the same covariance matrix, that's inverse, or you can say error matrix, whatever you call it, into x minus mu. So this expression x minus mu whole square has changed like this. So with two variables, then it is much easier. It reduces to this type of expression, that 1 over 2 pi square root of 1 minus rho square, rho is the correlation coefficient, and exponential this function, 1 divided by minus 1 divided by 2 into 1 minus rho square, and multiplied with x square minus 2 rho xy plus y square. So if we see here that how they are related, so here you can say they have positive correlation. Okay, so that's why these ellipses are sort of tilted in this direction. Positive, both are increasing when x increases, y increases, or x1, x2, whatever you call it. Then I come to Gaussian quanti. So quite often actually, since it is symmetric, what we do is that we sort of scale the variable. We scale the variable in the sense that x is, we subtract x0, the average or mu value, whatever you call it, from x, and then you scale it in the sense you divide by the uncertainty in measuring that. So this is the expression x minus mu by sigma, and you call it z, for example. And then if we do the same plotting, after all this is a function of x only, then we will say we will get the symmetrical distribution now centered around 0. And these are 1 sigma, 2 sigma, 3 sigma, 4 sigma, 5 sigma, etc. In principle, Gaussian distribution ranges from minus infinity to plus infinity. And if we try to find out the area, if you remember, the total probability should be 1. So the area under the whole curve is 1. But now if we consider only the area under the curve around 0 within the range plus minus 1 sigma, then we will consider as if it is mu plus minus 1 sigma, and that area is 68.3%. And so in terms of z, the same expression for Gaussian distribution, it comes as much simpler one, 1 over root over 2 pi, because now sigma is 1 and e to the power minus z square by 2. Just see here. X minus mu by 2 sigma, x mu is 0, rather x minus mu by here has become, mu by sigma has become z. So that is why you will get this expression, z square by 2. Now we want to talk about cumulative distribution because we want to find out the total probability starting with certain value. I guess later these things will be covered again. So I am not going to discuss that. So you take from minus infinity to certain value of z. Z equal to minus 2, minus 1 or whatever it is. And what you do is that you integrate out up to that z value. So the cumulative distribution of the original Gaussian function and the standard Gaussian are related like this. So essentially my phi z, because we are we are using this variable z now, transform variable z, we are not using the expression, rather notation capital Fx, etc. So we call it phi z, and they are essentially the same. So z is often called, it is rather used to express the deviation of a measurement from the mean. This is a deviation of a measurement from the mean mu. Okay, and we can talk about it for p-value, but I think today I'm not going to talk all this. P-values, I think again later it will be covered by somebody else. So coming to various aspects of Gaussian distribution. So if we have the same mean but different sigma values, after all the area under the curve should be conserved. Total probability is 1. So if we increase the sigma, full width at half maxima, or basically if you say in our measurement that value sigma, the measurement error is large, that means sigma is large, then how it will be distributed? That sigma large means you take let's say the central value is 10. If sigma is 1, then okay, between minus 9 and 11, 68% of your measurements will be there. But if sigma itself is 2 or 3, then it will be spread out. So this is what it shows, that if sigma is large, then this curve becomes flatter and flatter. It continues to remain symmetric around the mean value, and but the height comes down. Area continues to be 1, area under the curve, be it for blue curve, this pink curve or the red curve. Okay. And now we try to say, after all we have been saying that it is 1 sigma, 2 sigma, etc. If you remember here what I showed. This is 0, 1 sigma, 2 sigma, 3 sigma up to 5 sigma. Similarly, minus 1 sigma, minus 2 sigma, minus 3 sigma, and so on. So if we try to plot it, then we will see that if we don't shift it and take it at a mu value, then mu plus minus 1 sigma covers my 68% of the error. So each half between mu and mu plus sigma, the area is 34%. Similarly, mu minus 1 sigma, the area is 34%. Okay, so the sum between plus minus sigma is 68%. And then what happens is that if we extend it to 2 sigma plus minus 2 sigma, each one we are getting about 14%, 13.6% addition. So this is what is done here. That means the area from minus 2 sigma, mu minus 2 sigma to mu plus 2 sigma, the area under the curve, if you sum over, it becomes 68 plus about 27, let's say. So that is what is 95. So n equal to 2 sigma, the area is 95%. So that also gives us some, if we say that, okay, I have made a measurement and this error is so and so, so the central value is mu plus minus sigma, then we can say that if we do a large number of experiments, 68% of the time, the value should be remaining within that. If we want to take chances and we want to be more confident, then we say 95% confidence level. What does that mean? 95% confidence level means you give a range and you say that my real value must lie within that range. Okay, so that is what happening. 1 sigma, 2 sigma, 3 sigma, and then 5 sigma onwards. You can remember these numbers because this will be always useful. And when it comes to confidence level, that means 95% of the time the measured value will remain within plus minus 2 sigma. And almost 100%, but it is still, you can see 997 accurate, is within plus minus 3 sigma. But since the Gaussian distribution extends from minus infinity to plus infinity, there is tiny bit of amount of area still there. And so the point is, if we extend our integration to plus minus 4 sigma, then the probability is very, very high. And what is not there, the probability which is missing out is 6.5 into 10 to the minus 5. That's the only probability remaining. So the area under the curve within mu plus minus 4 sigma is 1 minus 6.5 into 10 to the minus 5. You can stretch further and you can see here most of the area is already contained within plus minus 5 sigma, only up to 6 decimal place is the same. After that, very little bit is there. So when we say that we have discovered something with 5 sigma significance, what we mean is that if something is here far away from the central value mu, what is the probability, like we were saying, that it is fluctuating and showing up in this area. When we say 3 sigma observation, that means above the background, okay, let us say this is the background level. Above the background, we have 3 sigma significance, means our excess of events, you can say above the background, the signal has large probability to be correct. What is that probability? That is 99.7% of the time it will be correct. But still that 0.03%, 0.3% remaining probability, that corresponds to, okay, background may fluctuate. So that's why we don't, if we want to claim something as discovery, we go for 5 sigma significance. That means that it is far away. 5 sigma is far away. And the probability that the discovery is correct is so high. It is just 1 minus, it is Total probability minus 5.7 into 10 to the minus 7. We were talking about central limit theorem. So central limit theorem is that there are many independent random variables in real experiments, but at least approximately there will be, they will follow a Gaussian distribution. Most of the independent random variables in experiments, they follow Gaussian distribution. So when these independent random variables are summed up, they are properly normalized sum tends towards a normal distribution. So what do you mean by normal distribution? This is my normal distribution, normalized. Why? Because you have subtracted the average from the x and you scaled by the standard deviation. So this is my normal distribution. And the original variables, they need not be normally distributed. Sometimes they can be distributed by according to Poisson distribution, sometimes according to binomial distribution, so on and so forth. But if you take the large number, then everything follows Gaussian distribution. So this is mainly due to the central limit theorem that allows to approximate the sum of multiple random variables regardless of their individual distributions with a Gaussian distributions. And Gaussian PDFs are frequently used, that's why, to model the detector resolution. When I say, okay, I can, I have a precision in the voltmeter about 0.001%. So when we say this precision, that means we are talking about Gaussian distribution. That if you make large number of measurements, and the precision will be that the error it refers to. So if we take sum of n independent continuous random variables xi, each has mean, because they are independent, so their mean values are all independent mu I and the variances are sigma I square. So in the limit n goes to infinity, a Gaussian, there will be a Gaussian random variable. It has the mean as sum of that, and variance is sigma square, which is given by sum of the sigma I square. So the total error is given by the sum of them. So quite often you will see that when in some measurement is quoted, let's say we were talking about m in the morning, m plus minus some value, again plus minus some other value. So what does it mean? It is in quadrature. It is a square, you have to take it, remember. So one component is the statistical uncertainty, another component is the systematic uncertainty. When we measure something, we have to take care of the statistical uncertainty and we have to take care of the systematic uncertainty. But when we want to say that it is error is something, then you have to add in quadrature. This is what we mean. So this means practically regardless of the original distribution, the average of the mean for many measurements is Gaussian. And the statistical error behaves like root over n if n is large. So that is why if you take large number of, let's take you have done 10 measurements, so the error is more than 3. You take 100 measurement, error is, so fractional error, you can say it is square root of n by n. So that means 1 over root over n. So when you talk about the fractional error, if you take 100 measurements, then it is the square root of n is 10 and fractional error is 10%. So now if you take 10 to the power 4, then the fractional error is only 1%. That's how it goes. Okay, I don't have many slides other than this last one. So this is about chi-square distribution. So chi-square distribution is something I felt is quite important because it is useful for testing the goodness of fit. We were talking about the fit. We have some data and we want to approximate it with some probability density function or with some functional form. So let's say something you feel it is distributed according to linear distribution. I feel it is distributed according to some polynomial. So how do we test? What is it that actually the data is following? To do that, we will do a chi-square test. So this chi-square test is that if there are n independent random variables, so these are the, you can say, corresponding to each observation OI, there are, I made a mistake here. It should be, okay, OI plus minus delta Y. I will correct the slides. So after all, this is distributed as Gaussian densities with theoretical mean mu I and standard deviation sigma I. Then OI actually is associated, each measurement is associated with an error, let's say delta I or something. Then the corresponding observation is OI and the expected value is EI. What we do here, we try to take the difference. OI minus EI, square of that, and then we divide by the uncertainty in our measurement. So this is our measurement, this is our expectation, this is our observation, you can say, and this is our expectation. So you take the difference, square it, and you divide by the square of the variance, and you sum over all the I values. What you get is that chi-square. Now let us say my theoretical expression has 5 parameters. Let's say it's a polynomial of degree 4, it has got 5 parameters and so on and so forth. And my observation is, there are 20 observations, I have 20 points. So what is the degrees of freedom? Degree of freedom will be 20 minus 5, 15. Just remember this. I have 20 points, 20 observations. For each observation, I have some theoretically expected value. But that value depends on 5 parameters. And I want to find out those parameters. Once I find out that parameters, I am fully in control of the theoretical description. Agreed? That I am writing a functional form which is based on 5 parameters, and I am interested in finding out those parameters. And I do the measurements. So my degree of freedom will be total number of observation, and then you subtract from it the constants, number of constants. So that is given as k, degrees of freedom. So my chi-square k is equal to sum over y minus ci square divided by delta I square. I have written it wrongly here, I will correct it. So by doing this, what we do is that we measure the reasonableness of fluctuation in data. Now, if my chi-square is large, is it good or bad? Can somebody say? If my chi-square is large,
Should be good only.
should be good. Think about it.
Bad.
That would be.
It will be bad. Correct. Why it is so? Because you see, that means this denominator is, of course, you are dividing by the error. But the numerator has observation minus expectation. Chi-square large means this is large. That means my observation is far away from the expected value. That means my theoretical description is not really correct. Isn't it? So it is, that means my whatever I am trying to predict theoretically, that prediction is not good.
So I have a problem with this reasonableness of fluctuation.
Tell me.
Ma'am, the reason why I told it would be, of course, mathematically whatever you have explained is making sense. But what does this statement like reasonableness of fluctuations in the data mean?
So sometimes what happens, you also know that maybe something is, you know, definitely this measurements follow so and so distribution. Now what happens is that if my fluctuation means, if you remember, let's see, in the morning I showed something. Let's say here, look at the fluctuations. Each point has large amount of fluctuation. With this is a central value and this is the error. So here if I try to make a fit, I take observation and I take the expected value. What is my expectation? E. OI is the point. And this is the my error. So I try to find out whether my theoretical description is okay within the fluctuation. Say for example like here. Sometimes it is shooting, the data is shooting up. My theoretical description gives me this blue point. And roughly my observation is following it. But if the fluctuations are less, that means these error bars will be less. Okay?
So
that means if the error bars are less, by doing this chi-square fit, I will modify my parameters, input parameters of the theoretical description such that this blue curve will be tweaked a bit to fit the data. Now, if the errors are very large, that means I have lot of leeway. Agreed? My parameters in the theory, if I take this here and the central value in the observation was here, I would have liked that the center of observation sits on this one, histogram on top. For this bin, this is the value. It's a frequency distribution, let's say.
I'm trying to understand, ma'am. So I really followed the mathematical description. I'm trying to understand this picture here. So let's say in the first part, so I have seen there is this histogram kind of thing that is there. This is a distribution though.
Frequency distribution, let's say some variable is there. Okay.
Yeah.
Then?
So what does it imply? For example, around 80 or 90, the values, the experimental values are inside this distribution, and for some of the things, the experimental values are outside this thing. So could you please explain what does this point mean, and that is around 90, and the point right after the 100? Could you please take these two examples?
So what does it mean? That here, of course, the histograms have a very small binning, but the experimental data, you can see number of events are very, very low. 1, 2, 3, 4, etc. The experimental data has large fluctuation, but still within fluctuations, experimental data is able to, this is a broad statement, is able to describe the theoretical expectation. Now what is happening?
Yeah, in the
in
case
80 there is not even any point is there.
Yeah.
There is nothing there. Take for example 90.
Yeah.
Okay. This 90 it is going up. We can see in data also the same trend.
Yes.
It started with some value, then it goes up. And then it comes down, but the consecutive bins here, they have same central value.
Yeah.
And this central value is far away from what the theoretical expectation was.
Yeah.
This is the theoretical expectation is at value 3 and the experimental data says 5.
Okay.
So it is even at this bin value, it is even beyond 1 sigma. These error bars corresponds to 1 sigma. Okay.
Yeah.
I was talking about Gaussian distribution 1 sigma, 2 sigma, 3 sigma, etc.
Yeah,
That's in terms of probability. Now, I told you that each independent point is distributed as a Gaussian distribution. Each independent one. Be it at this point, this point, this point, this point, everything.
Yeah. Got the picture, ma'am. Let's say now we are in the same discussion. So in the sense, the ones around the 80 and 90 will have a less chi-square value, and just after that, having a 2 consecutive experimental values to be at 5, the first point around 90, this point will be having a very comparatively less chi-square value than the point
contribution to the chi-square, total chi-square will be less.
My understanding, right?
Yeah.
And
that difference, you are scaling by the error. This is the uncertainty. This is 1 sigma.
Okay.
So the difference, if you see the difference of this versus this, is roughly equal to this value.
I'm just comparing
the theoretical expectation. Let's say it is at value 11. The blue.
Yeah. But the
and the experimental is at 8.
Yeah.
So the difference is 3.
Okay.
And I am saying the 8 has statistical fluctuation, fractional one you can say, is also similar value, about roughly about 3.
Yeah.
So if I take my expression here, this I'm wrong here. You have I have to put here delta y or delta I, let's say. That is each y plus minus delta I. So I am scaling again. The difference between the observation and the expectation is scaled by the uncertainty.
Okay.
So at each point I am roughly expecting a unitless or whatever you call it, a value 1.
Because it's well defined.
If it is a good one, if it is a good fit, maximum 1, or you can roughly say, and then you sum over n points.
Yeah. So that's.
And then you get it.
Can you take?
And the reduced chi-square, there is something I didn't have down. Maybe I should have elaborated a bit. If you go for the reduced chi-square, that is this total chi-square summing over all the points, and it is defined by the k degrees of freedom. K is less than the number of observations you have. By how much amount? It is the number of parameters you have in getting this EI. Let's take a linear fit, y equal to mx plus c. Yeah. So how many points do you need? Two points you need, and you have got two parameters, m and c.
Yeah.
So now you are trying to fit it.
Okay, got it.
Got it, no? So is it clear to everybody what is chi-square? So and you take, sorry, tell me.
One last question. Can you do that plot where you have different experiments, ma'am?
Yes, so, I think, no, not this one. It's here.
Yeah.
No.
Not this one.
I think
the morning.
Here. Yes.
Yeah. So now the one just before this 100, maybe 95 point and 93 point. If we calculate the chi-square value for this point, which is having a theoretical value of
chi-square value will be sum. You are trying to take a global picture. What is the sum of the total deviation? No, it is not individually.
Okay.
So fluctuate can happen, because if the numbers are small, very few numbers, we just now discussed, the fluctuation goes as root over fractional 1. So the less number of points here, of course, all are very less number of events. So the fluctuations are large here. Now if the fluctuations were less, if this frequency were very high, number of events observed, then these statistical uncertainties also will come down. So this point will be central value plus these error bars will be less. That means if I want to fit a distribution, theoretical distribution, given by blue curve, I have to tweak the parameters of that blue curve.
Right. So if I understand it correctly.
So in this case, it is not the case. I just sort of you think. Tell me.
So this is my interpretation somewhat.
Yeah.
So the chi-square distribution, if somebody gives you a data and then asks you to find a distribution, first we will start off with whatever distribution in your mind.
Yeah, exactly.
And have the parameters, fit that, and calculate the chi-square value.
Chi-square. If it is too large, that means it is not good.
Yeah. Then you can live with the distribution. If that is not there, you can live with. You have to try another types of distribution and
exactly.
And go on like this and find out what exact distribution you are.
What is the best distribution? Which distribution describes your data best? So this is one thing. Another point is that if you take let's say polynomial of degree 6, 7, 8, 9, etc., then you have many number of constraints. Then you don't have too much leeway, too much free hand to vary, because you have got only 20 points, let's say 20 observations. So you have to make a judgment. If I have 20 points, what will be the degree of polynomial, but what will be the degree of the now what will be the number of free parameters which describes my data in the theoretical distribution.
Okay.
And now my idea is that from chi-square fit, again let's say y equal to mx plus c, what I do is that I try to find out, I tweak the value of m and c to fit the data best align. So what is my best data? After fitting I get some value. This is my best fitted value. We will see for a maybe those things I will include it. I'm sorry that I didn't spend much time preparing these slides. I was notified only 3 days back. So for each one, let's take y equal to mx plus c. Say for example, you keep on varying m and you keep on plotting chi square. Then you will see for a particular value of m, chi square is negative. Chi square is the minimum. And quite often it is a parabolic distribution. That means chi square is increasing on both sides beyond the value of chi square minimum. So the value of m for which chi square is minimum, that is the best fitted value. And for to get that, since you have two parameters, you have to keep the value of c constant. You get this. Take it as independent variable. So you keep on varying m, you find the chi square, and then you see that for which value of m the chi square is minimum, that is your fitted m. Now fitted m, again we have to find the error. How will you get the error? So again the standard method is that I said that this is a parabola. This side is my chi square and horizontal is my m value, which m value I am changing and I am plotting the chi square. It is increasing, decreasing at various values of m, and we got a parabola like this. I will put that distribution in the slides. I am sorry I don't have it now. So now you got m0 for which chi square is minimum. Now you vary m such that chi square changes from chi square minimum to 1. Because both sides it is increasing. So the value of m on the left side of m0, that is my negative range, and the value of m on the positive side, there also chi square has changed by value 1 plus 1. That is the upper range of m0 or m. So m0 plus minus 1 sigma, when we say, that is obtained by minimizing the chi square and by varying the value of m, whereby the chi square increases by value 1. I don't know whether it is clear. Does anybody have? Tell me.
Ma'am, can you explain in this picture that is there?
No, this is actually this picture is not the one to talk about the chi square minimization. I have a feeling that this will be all covered in your parameter estimation in the coming days. No. But I will also try to put in some way that what we mean by chi square minimization. Likelihood maximization. I think all these are coming.
Yeah, so I can actually see we can formulate it as an optimization problems wherein
yes, it is optimization. Yeah,
we can find out those parameters in the distribution which you have.
Exactly. So basically, that is why this chi square is very important.
In such a way that we can minimize the chi square.
Yeah.
So up to that part, I'm okay. When we are talking about the parabola and having a minimum values at the two sides and then summing up.
That I think your slides in the coming days you will be explained about those. But you can have a look at it, chi square minimization somewhere in the books. I will also try to find some reference.
Thank you so much.
So basically, chi square statistic is a measure of the difference between the observed and the expected frequencies of the outcome of a set of events or variables. Okay. So you are summing over all it is over the set of measurements you have done. It's not just at one point. And of course, chi square depends on the size of the difference between the actual and the observed values. The degrees of that is my upstairs, this one. The degrees of freedom, of course, how many are there, as I told you. That if the degree of freedom is less, then you are more constrained. If you have only 3-4 points, and you have let's say even two parameter fit, still it remains you don't have too much leeway to change this m and c in the linear fit. So then the differences can be high, and sample size, of course. observed values, the degree of freedom, and the sum. So if you have large number, then you have a lot of freedom to tweak your parameters of the theory. That's the idea. Also, as I said, it can be used as a test to test the goodness of fit between the observed distribution and the theoretical distribution of frequencies. Now, having done that, chi-square follows a distribution like this. It's a bit complicated, but just see. This chi-square, this is a variable now. And that variable has a probability density function like this. You remember k here is the degree of freedom, and gamma function is something defined in terms of error, etc. You can have a look at it. So it is only possible for positive chi-square. Chi-square cannot be negative, remember, because it's all square. And that's why it is plotted like this. So this is just for your information, how we do it.
So what are the, applications?
Advantages.
Applications can directly use the chi-square distribution, man.
So the
chi-square metric for finding out whether the distribution which you have assumed, and
that is one aspect. That is one aspect that you are trying to find out the how the goodness of the fit is, etc., etc.
Yeah.
Okay, and this is just an information that how the chi-square is distributed.
Okay. And aren't there any applications of which follow the chi-square distributions directly, ma'am?
Yes, but I think.
Yeah, I vaguely remember there are some.
Yeah, I do not remember now.
Yeah, they directly follow the chi-square distributions. Yeah, okay, fine, I'll figure it. Thank you, ma'am.
Yeah, I will also try to find out. I will add up in the.
Because when the distributions are discussed normally, we will also see as chi-square distribution also as one of the distributions, and there are physical cases where the experiments, the points which actually measured will fall under the chi-square distribution directly.
Not so much. Not so much.
Oh yeah, some at least some of parameters.
Parameters are to be obtained by chi-square minimization procedure. That is what I tried to explain.
Yeah, that was very
so
clear.
So that is okay. But typically, I think mostly it is. No, I don't remember any particular application of this chi-square distribution.
Sure, no problem.
I'm sorry, I don't remember.
No, that's okay. Thank you.
So if you give up on the exponent part, you can just see it is a deviation, that this first part.
Yeah.
First part is the deviation from the theoretical mean and divided by the expected dispersion. This one. And this is nothing but the same x, whatever is written as x, that is actually chi-square here. I picked up from different sources, so the notations are different. I will correct them up. All I am trying to say that with increasing degrees of freedom, the chi-square value is also increasing.
Degrees of freedom,
this is K9, let's say here.
Yeah.
This is the probability distribution, and this is the whatever is x. This is the chi-square.
Yes, ma'am. So we can see that for k is equal to 9, the chi-square
value will be extended to much larger values.
Maximum value it can attain is 0.1.
That maximum will not be. After all, this is a probability density function. So what you have to do is you have to integrate it out, and that integral should be equal to 1. Number of degrees of freedom k, it increases means you have more number of observations, and so definitely this chi-square we'll have contributions. This is sum over I.
Yeah, yes.
So that value, that's why it will keep on increasing. That is why what is typically done is the reduced chi-square. So you divide by the value k, or the number of degrees of freedom. So if I have 20 observations, roughly I would say that my reduced chi-square should be roughly equal to 1-ish. Because you have taken care of this increase. If you sum over 10, you have contributions from 10 points. If you sum over 20, you have contributions of additional 10 more. So this chi-square will increase. But that does not tell me much how is this doing, observation and the expectation value. So that is why if we divide the total chi-square by the number of degrees of freedom, then I will roughly get an idea that overall, if it is 1-ish, overall that means my observation is matching with the expectation. Is it clear? If the reduced chi-square means total chi-square divided by the number of degrees of freedom is 1-ish, because if I do not specify that I have taken data over 30 points or 50 points, and if I just quote this chi-square, then it is not giving the full information.
Correct. So it's kind of estimate of mean also. When we are doing that, we will have.
So if the reduced chi-square is large, then we will worry about that. Okay, observation is varying too much from the expectation. But reduced chi-square is 1-ish means it is good.
Yeah.
That's it.
I was just looking at this right-hand plot, ma'am. This I believe the K's are the number of degrees of freedom, right?
Yeah, K's are the number. Yes, correct.
Just looking at this probability distribution itself, the red one, with the K is equal to 9. So
it is terminated, but actually it will go on till high value.
So I've just maybe my interpretation is wrong. So if I were to find out, let's say at in the range of 7 to 8, x value of in the range of 7 to 8, if I want to find the probability, because it's a probability density function now.
Probability density, you have to fix up the K.
Okay, I'm looking at K is equal to 9, ma'am.
K equal to 9, okay, red curve, yeah, fine. Yeah.
So K is equal to 9, and I'm trying to figure out this x probability that this x falls under 7 to 8. And for the another K, which is K is equal to 6, I'm looking at the same value. I'm trying to find out the probability. Which one would be more and which one would be less, ma'am? From plot it, I can see that.
K equal to 6 is reduced. Fx is less. Already this magenta curve, K equal to 6 is less.
Oh, I can directly read this. I can interpret something.
You can do like that, yeah. Though I think it is not really the way to sort of read these curves. It is basically trying to say that how the chi-square will be for different values of degrees of freedom, and maybe it will be good to have this whole thing completed. I will look into the internet. There, I'm sure there will be some other distribution.
Yeah, I'm trying to see how can we read these graphs, or can we actually get something of this sort information from this thing. Yeah, I do agree that that depends upon what functional form you choose. That decides.
So now let us say that chi-square, if there is only 1 degree of freedom.
Yeah.
Okay. Then chi-square is going high up, Fx. That is good. With 1 degree of freedom, it's mostly 1. The area under the curve, if you...
Yeah, area under the curve is more for the K is equal to 1 case.
1, exactly. That is the idea.
Oh,
similarly, for K equal to 2, you can see that it is spreading over. Chi-square can be large, but the probability for chi-square, let us take a K equal to 2. Okay. So for chi-square value to be large, this x is equal to this chi-square, that probability is very low.
Okay, now maybe I got an idea of how to interpret this question. We have to look at the holistic area under the curve only.
Exactly. Because this is the density, you have to take the integral.
Okay.
So, very large value of chi-square for K equal to 2, the probability is very low. And for K equal to 1, Let's take chi-square value of 5. Chi-square value of 5 is very less probable for k equal to 1. Slightly higher for k equal to 2. But if you go for k equal to 9, it's okay. It's not too high.
Yeah.
Because you have k equal to 9, so it is supposed to be going that side, beyond that side.
Yeah, yeah. I don't know, ma'am. So this comes back to the selection of the distribution function again.
Yeah.
That essentially means that if you have less and less parameters in your distribution that you are going to predict. Let's say I have 12 data points, madam, and I have 3 parameters in my to be estimated in the distribution.
Yeah.
Or let's fix it to, because most of the distributions have 2. So 12 minus 2 is
Let's take
equal to,
Gaussian distribution. You have mean and the sigma. And from the 12 distributions, you have 10 degrees of freedom.
degrees of freedom. Now, so how in that case? 10
So
degrees
you are tweaking the mu value. You are also tweaking the sigma value. When you do the fit, when you do the chi-square minimization, by degrees of freedom, what we mean that how much freedom I have in shifting around. Because if you let us go back again, you have to again, as you said the word holistic, you have many points.
Yes.
So if somebody is going shooting up, somebody is going down, overall you are looking at the situation. You don't mind this point shooting up. You have many degrees, but you have only, if you have only these few points, then you cannot afford to vary too much.
Good evening, ma'am.
Yes.
Yes,
good evening. Tell me.
I am Dr. Vijaynath Pathak, Department of Faculty, W Professional University. Ma'am, my question is how I have also conducted research to how can use like a parametric and non-parametric the chi-squares regarding the nominal.
Shall I go to the last slide? Chi-square distribution only?
Okay.
No, sorry. What was your question?
Ma'am, my question is how can use an ordinal scales regarding the chi-squares, regarding the age distributions as compared to the other scaling systems like ratio scale as well as the ordinals like female and females and age groups or internet addictions related to how can analysis these types of the data.
So it depends on what exactly you want to show. So give me a problem, well-defined problem. You are saying, say for example, what did you say? Male, female. What you want to know about male, female?
Male, females is related to the, like age group. Which age is more? Which age is more used for the internet? Like suppose that. And
take one group, okay? Female. At which age people are more addicted towards internet? That's what you want to say. So.
Yes.
Roughly you think, okay, lower the age, maybe they are more addicted. Let's say. So you feel it's a linear distribution. You have some data which is distributed all over.
Yes.
So looking at the data, you see whether is it really correct what I'm saying, is it distributed all over or it is showing some trend. So you start from there. Is there some inclination? You are saying that the lower age, maybe below 35, 40, there is more internet. So you plot age as the x variable, horizontal variable. You take a measure of the addictedness, means how many hours one is spending. Don't take my words seriously. That how many hours a person is spending for get male, female, etc. Just take a person. Okay, a student in your college, let's say, or any person entering the college gate. So it could be anybody, teacher or the student, anything, so that you have large distribution. So you take the age on the horizontal axis and you take the number of hours spent on internet. So you plot it. So your independent variable is the age. Your dependent variable Y as we call it, or fx, whatever you call it, is the number of hours spent. Okay. Now you say that, do you think that we at certain age it will be increased? Let's say at the age of maybe 23, 24, when the students have already got admission in the college, so they are not studying so much. So in that case, maybe you expect a Gaussian type of distribution. Maybe. Or you think that with increasing age, say beyond 24, 25, it is falling down because they are busy, they are joining jobs, their job demands are too much, they don't have time to look at the internet so much. Like that, you try to say, or you can say it is continuously falling after, say, 25. So up to 25, it is increasing. So you can describe two different portions of your distribution by two different functional forms. Like in the first class, I showed in the morning class, I showed that you can combine a delta function, if you remember. Where is that?
Okay, thank you, ma'am. Thank you very much.
So here, so you take like this, and you try to find the trend of your data, and from there you can try to find it. Maybe a polynomial or linear or any other function. Okay, fine. Any other question? Anybody else wants to ask any other question?
Ma'am, you were something talking about degree of freedom. So please, ma'am, can you elaborate it?
So degree of freedom means, as the name suggests, how much freedom I have to modify my theory. See, morning I was telling you that you take prior probability, you posterior probability. Again, it is similar thing. You assume something to start with. Like just now we were talking. Age versus number of hours spent on internet. So you think that it is a linear here. With increasing age, maybe it is increasing. Let's say it is increasing between the age of 7, 8 till 25. The internet addiction is increasing, number of hours spent is increasing. But then you can say no, when the student is going to higher studies, it is increasing exponentially. So to start with, you can do a fit or try to find the chi-square corresponding to a linear distribution. Another time, you do a linear distribution, means it's a polynomial of degree 1, y equal to mx plus c. Next time you say no, I will take a polynomial of degree 2, y equal to a plus bx plus cx square. Now you have got, let's say, 50 points. When you have 50 points and you have to fit all these 50 points, you have theoretical expectation. So in all these 50 points, you fix up m and c. So you calculate the value of y equal to mx plus c. But then, what will be the value of mx plus c to be followed by all the 50 points? There are only two constants. So you have 48 degrees of freedom, means you can change this value of m and c to get the best chi-square. Maybe 10 points giving you some value of m. But if you have 50 points, you can change around those m values. Now if you have got a polynomial, you have to now fit 3 parameters. So instead of a, you take a1. Instead of b, you take b1. And then you see how your data is fitting with the expectation, the theory. And again, you have to take the holistic approach. You have to sum over. By changing a to a1, b to b1, some of the points will be far away from the observation, will be far away from expectation. But some other points will come closer. Then you have to see what is the total chi-square. Because you are summing up. What is the total difference? So if you have more points, you have more degrees of freedom. Because you can change slightly and you see where the change is coming into effect. But if you have only limited number of points and you have large number of parameters, to fit, to be determined, then you don't have too much free part. Take the straight line. You can tilt the straight line. You are tilting the straight line means your aim is changing and your intersection with the horizontal axis, that is also changing. Agreed?
Yes, ma'am.
So, if you have only 2 points or 3 points, or let's say 5 points, so the straight line has to go nearby those 5 points. But if you have 10 points, then by tilting, straight line will change, but they will be okay within 10 very different observation points. Means you can tilt the straight line more freely. Do you agree? Think about it.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
So this is what we mean by degree of freedom. That you have number of observation, 10 observations, and you have 2 degrees of freedom. So there are 8 ones. Because effectively, for each EI, you have to follow the same rule, y equal to mx plus c.
Yes, ma'am. Got it.
Okay.
Thank you. Thank you so much.
Okay. Any other question? Anybody else?
Anybody else for the questions? I think, ma'am, no questions.
I think that is all. Yeah, okay. Yeah. I'm sorry for poor quality of the slides. I did not spend much time in preparing that. So I will try to improve and I will share it later.
It was very good, ma'am.
Thank you for the kindness.
Thank you so much, ma'am. Actually, you joined. We have sent you the request at very end of the.
Yeah, and I thought my old things I will be able to do it, but that was in PowerPoint, and I use now completely Linux, so I could not do it.
But you accepted our invitation, and that was a very big relief for us.
No, this is our duty also. This is our duty to be able to help out to the students as much as possible. But to the students, I want to make it a request that just attending this workshop for 5 days is not enough. Yeah. You really have to do lot of homework. You have to, and fortunately enough, you have the books, the libraries, and also internet. There are a lot of resources. So do look at them. Okay, thank you all. Have a good workshop for the next 4 days. Bye.
Thank you, ma'am. Thanks a lot. Thank you so much, ma'am.
Bye. Thank you.
Thank you so much, ma'am, once again. On behalf of Department of Physics, NIT Jalandhar, we are thankful for your time and information shared with us. Now, with this, we come to an end of today's session. Thank you all for your patience and cooperation. I request you all to please fill out the feedback form. The link has already been shared in the feedback in the description box as well as in the WhatsApp groups. So hope to see you tomorrow at 11 a.m. for the next lecture. Good day. Thank you, ma'am, once again.
Thank you, ma'am. Ma'am, thank you very much for this kind of excellent lecture for us. Thank you very much, ma'am.
Thank you, ma'am.
Yeah, thank you, ma'am.
Ma'am, you're not audible. I think you're trying to say something. Ma'am, you're not audible.
Oh, no, I'm saying that it was a good opportunity that I started preparing these lectures again newly. And then it may be useful for other occasions also when the students come to us as well. Yeah.
Ma'am, with kind permission from the honorable organizer, sir and ma'am, would you please be kind to me so that I can be in your touch through email for this particular,
Yeah, I have given the email ID. Okay, my name is Kajari Majumdar. So majumdar@tifr.res.in. You can send me mail. No problem.
Okay, ma'am.
I'm available. Yeah, no problem.
Okay, ma'am. If you please don't mind, would you please be kind to write down the email address again on the chat window? I guess I'm
let
not
me
getting
see.
it.
Okay. Yeah. Okay.
We will share this.
Yeah. MAZUMDAR at tifr.res.in India. Okay.
I guess.
I sent it.
It's not in the chat window here, but over there in
meeting chat. Meeting chat. It says. Which chatting I should use?
Yes, ma'am. It has just come. Thank you very much. Thank you very much. Thank you very much.
Okay.
Thank you very much, ma'am. Thank you very much, sir. Thank you very much, ma'am, for organizing such an event. Thank you very much.
Excuse me, ma'am. Hello.
Yes. Tell me.
Am I audible?
Yes.
Good evening, ma'am. Ma'am, whatever you have shared through the screen, the materials, we will be getting through mail.
That the organizers, I will send it to the organizer, but it will take me some time. Actually, this week I'm a bit busy, but I will make it, correct it and put in some more information. And then I will send it to the organizers and they will do whatever they want.
Ma'am, no issues. The time is not the matter. Actually, at last, if we get it, then it will be okay. Actually,
Yeah.
It will be beneficial. Thank you.
Yeah. That the organizers
Yes,
will
ma'am. Please do share this.
I will share. Sure. Okay.
Ma'am, please mention some of the books to be read.
That I have to look at it because typically we are concerned for a very limited crowd, in the sense with limited interest for high energy physics. But I have cut out in the afternoon the examples I was giving for these distributions, etc. So I will see what are the books available. But the books, I will also do the internet search. You can also do the internet search. I will still try to find out if there is a suitable book for beginners. Yeah. Okay.
Okay, ma'am. Thank you.
Okay. Thanks. Bye.
Thank you, ma'am.
Thank you, ma'am.
Okay, thank you.